Okay. I'll just finish setup while maybe a couple people trickle in. Uh, Not paying too much attention to what I'm saying right now because this is a part that I'll trim out of the VOD anyway. The vertical stream is going to be trippy during this part, but I think it's fine. I wonder, okay, I don't know how to do that part. We'll cross that bridge when we get there. We will cross that bridge when we get there. Okay. Wonder how long I should wait. The other times I had some viewers pop in the first minute or so. The other times I also had some setup to do, but this time I was pretty responsible and did most of the setup before. So let's mess with my camera a little bit. Put myself a little bit higher in the frame, a little higher still. Nope. Too high. Okay. Maybe there. We got my hair. We're going to see me looking down a lot. When I look right at it, I see like this. Okay, yeah, that looks good. Okay. Hey, I think if you are willing, concurrent viewer, if you could say something in the chat like a 1 or something. Uh, just gonna wait a little longer to hopefully grab like maybe one more person before we start. I won't wait longer though than like, what time is it now? Womp womp. Oh, it's you. Yeah, I think I'll give it like 2 or 3 more minutes before I jump into intro. This is the one tricky part about starting a stream. Um, I considered going live. Actually, I wanted to go live at 3:50 because then I would be like starting the content at the scheduled time, and I'd also have a 10-minute buffer to see if I could get anybody in here. Because that's the tricky part about live streaming is like when to start. I mean, the nice thing though is the thing that I have cooked up for the start of the stream, I think should be decent shorts content, even if the stream is pretty empty for that part. It will be a bit of a bummer because like I would like to get clicks on the shorts on the vertical stream just to see if it even works at all. Oh, by the way, are you on horizontal like laptop or are you on phone vertical watching? I'm curious. Because the vertical actually is okay on this Hugging Face Daily Papers. It's a lot less okay on the archive view, but it'll be good again. Like I've got papers, like I figured out the right zoom to where here I'll watch it pop up here on my little guy over here, but it should be like, yeah, like perfect. I get the whole paper on the vertical. I just have to be mindful of like where my head is on it basically. Oh, phone and landscape. Oh, so like not in the shorts viewer then, but like in the actual like regular YouTube stream viewer. I get it. I get it. Okay. Um, let's just start. And if we don't pick up anyone during this segment, that's great. I was kind of nervous for this segment anyway. Uh, because if I don't do it well, it's kind of embarrassing. Anyway, so the way we're going to start, first we're going to open a lot of papers. Kind of wanted to do that before, saved it for now. But right after we open a bunch of papers, instead of like last time where it's like over the course of a couple hours, I make it through all the papers slowly, I got a little timer, a 1-minute timer, and I am going to spend 1 minute on every single paper I open. That's the plan. And so it's like speed dating the papers. And that'll take us through the first like 20 to 30 minutes, depending on how many papers I feel like opening today. From that speed dating, we will decide if it's just me and like 2 other people, maybe it's really just me deciding. But in a perfect world, we would decide which papers to keep and look a little closer at, and which papers we've seen enough, they had their minute in the sunshine and now they can go right off into the sunset. So that's the plan. Open some papers now. Like usual, we've got daily papers, we've got ArXiv. Also, I opened a couple of things I just saw from friends, and also something I kind of missed last week because I don't think they published a PDF of this, meaning like I don't think they uploaded this to ArXiv. I think they just published it as a Hugging Face blog, but I still think it's interesting. So to get it to be shorts compatible, I exported it as a PDF. Now I've loaded it up, got it at like my ideal render, so we'll go through that. If I mean, I know I'm just talking to one person, but for anyone that watches later, if you ever want to, you're in the stream, you can just paste a link to a paper in the chat, an ArXiv link or a conference link, and I will open the paper and we can go over it live. At the size of the channel now, where I've just got like 1 to 7 people in the stream at any moment, I can basically look at any paper you possibly would want to send. So even if it's not recent, maybe you could get me to spend 1 minute on your bioRxiv paper from 2019. Probably, right? Do I have better things to do? I don't know. So at least 1 minute, you know, the speed date, we have the timer. We'll look a little closer at stuff we like. I'm not sure how pruned the list will be. I'm not sure how aggressive I want to be. This is kind of the first time. My main worry actually is just doing something cool with all these papers in 1 minute. So that being said, let's get started. As usual, I will grab the top paper of the week, just because lots of people voted for it. Must be something interesting in there, right? This is mentioning the clawbots. Kind of curious about that one. Let's see. LLM-based vision encoders. That's interesting to me also. Sorry to any shorts viewers. I don't think we have any right now, but if we did, I'm looking at one thing that you see and 2 things that you don't, to the left and the right of what you do see. I can't think of a way around that for now. When we're actually in the papers, you'll see the whole thing. So, okay. Long story generation, evolving. Okay, sure. Video streams, maybe that'll be interesting. Flash k-means. Okay, yeah. Speeding up k-means is fun. Thinking to recall. Nope. Bridging trust regions. Long context, geometric reconstruction with high. Ooh, okay, maybe. How far can unsupervised RLVR scale LLM training? No. Maybe. No. Okay, Omni diffusion. Okay, that sounds interesting. Navigation. Believe your model. Is this going to be vision or just reasoning? Okay, nope. Care edit, condition-aware routing of experts for contextual image editing. That sounds kind of interesting. Oh, did I not click intern VLU? Did I really not click that? No? Okay, well, I clicked it now. That would have been a funny one to miss. Latent world model, planning innate tokens. Oh, I saw that one during the week. Somehow it didn't end up on my list to click right now, but now it is. Video-based reward modeling for computer use agents. Why not? Unconstrained identity preserving video generation. Did we look at this one last time? We like almost definitely looked at this one last time. I'll speed date it though, because why not? I think we got it last time because it was in the 28 Feb ArXiv batch, which we pulled last time. But they submitted it to Hugging Face papers this week. That'll happen sometimes. You have like a 2-week window, I think, to submit it to the Hugging Face daily papers. So yeah, occasionally stuff will pop up here. I'll click it again. It'll be stuff we saw before. Oh well, that happens. This one might also be the same kind of thing, some video gen paper. Let's see. We're getting down into the 20 like territory. So I think Dream Video Omni control. Okay, video customization. That sounds topical. All right, so let's look at daily real quick just to see. We already looked at everything over 20 likes. Let's look at things below maybe if they're kind of high relative to that day, especially for this Friday where stuff hasn't had time to accumulate as many votes. Elastic latent interfaces. That sounds. I don't know what they mean by that, so we'll try to find out in 1 minute. I'm nervous. I'm actually nervous for the whole 1 minute thing, by the way. This is an idea more or less from a viewer. I'm going to do my best, but I might feel pretty stupid doing it. We'll see how I do. Omni stream. Ooh, perception, reconstruction, action, continuous streams. That sounds pretty interesting too. Anything else? Okay, we're getting kind of in the weeds now. Let's rewind a day, go into, ooh, this day just didn't have as many liked papers. Let's see. Laura's an LLM. Laura, video personalization. Maybe there's something interesting there. Can large models keep up? Continual knowledge streams. Okay, now we're below 10 like territory. Let's keep moving. Let's get down to our threshold. Okay, mini app bench. No. Ooh, wow, okay. That's interesting. I said Friday wouldn't have as many, but like maybe there were just like a bunch of like hot papers that dropped at the same time. Because we're getting like big vote drop-offs on these earlier days in the week. Streaming autoaggressive video generation via diagonal distillation. Okay, that sounds... Since I'm pushing a lot of video gen stuff lately, that sounds topical enough to where I'll pull it through. I see we have a couple more concurrents. Feel free to say hi in chat or just like type a 1 or something. It's always nice to see. In the back of my head, I always wonder, like, everyone that pops in are these real viewers, or like occasionally I get some bot coming in, just maybe like scraping things. I don't know. Although maybe the bot would be programmed to listen in type 1, so maybe that's a bad test. Anyway, if you came in, we've already opened a lot of things. You can see them at the top. I'm just scrolling through to see if I missed anything I wanted to grab. And what we're about to do here is speed date the papers. So I have a timer. The timer is 1 minute. And that 1 minute, my goal is to look at the paper. Oh, hi, Hudefa. So the goal is to look at the paper, see what it's about, communicate that to you. We'll see together what it's about. I'll communicate it all in under 1 minute. And at the end of that minute, we decide keep or close. If we keep it, we'll revisit it later. If we close it, it's got its minute. That's all we're going to do in the stream. That is the plan. I think it sounds like a good idea. I think it sounds kind of hard. I don't think I want to get anything else from Hugging Face. How many papers do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then 21, 22, 23. Okay, so we're looking for like a couple more. We got the EVA talk already, right? Somewhere in here. I'll open it just in case we didn't get it. I'm pretty sure we got it though. Programmatically verified benchmark for visually grounded deep. Okay, yeah, that sounds interesting too. Some of these are going to be redundant with the Hugging Face. If we get to them, we'll just close them. Also, apologies to any shorts viewers. I know you can't see this part. We won't spend very long here. Okay, video stream thinking, video LLMs. Geez, there's a lot of stuff that seems interesting here. Streaming visual-based spatial intelligence with test time training. I think I saw that on Hugging Face and didn't click it. For some reason, reading the whole title here makes it look more interesting. I know I have attend before attention open. This sounds interesting, mainly because it's taking generative and then doing some kind of like understanding-based task, sort of, or like a mid-level task, right? Depth is not necessarily semantic information, but it's also not the same thing as pixel information. So curious to see how this model did. From my experience, generative models are very good at this kind of thing, where the thing you're predicting is like albedo or something like very similar to the pixel information itself, at least at that level. Okay, so... Oh, and here's a unified token compression for joint generation classification. That sounds interesting. That sounds super related to the paper I put up like a month ago. Jeez, we're opening a lot. Let's rewind a day and just scroll the top. On this day, nothing is jumping out at me quite as much. I guess like I've actually been wondering the artistic style thing, so I will open that one. It's a question that's been in my head this week. This is a great time too. If you're in the chat, feel free to drop a link to a paper. If it's something you've seen this week, you want me to take a look at it. Like I said, giving all papers 1 minute minimum. That's the idea with this part of the stream. So we're opening them. Hierarchical visual understanding. Okay, that sounds interesting too. What day are we on? Wednesday. Let's go to Tuesday. Already have that open. I think I opened this one as well. And consistent video retrieval, visual state transitions. I'm curious what they mean by that. Okay, that's fine. Let's go to Monday. So we're about to start the speed date portion. I think I have a little more than 30 papers. So the segment will be a little longer than 30 minutes. Hopefully it's a good segment. Hopefully I don't fall behind and then it takes like an hour. I guess I have nothing better to do, so that's not a big deal. But visual explanations, I want to know what that means. Lots of benchmarks. Geez, so many benchmarks. We already got Omni Diffusion open. I don't know if I opened this one. That's up my alley. I actually was running some experiments along these lines, taking a Quen, running some images through it, and then taking like different tokens and coming up with ways to aggregate the tokens and just doing little linear probes to classify images. Some interesting things you'll find there. Like I found that the Quen VIT would give tokens where you can do pretty good. And then the output of the LLM, you can also take those tokens and do decent. But your best performance by a little bit comes when you classify something from like the first couple layers of the LLM. So you get deeper in the LLM, the classification degrades a little bit. You get towards the end, it gets a bit better again. But the peak is right a little bit past the VIT encoder, and just when you've entered the LLM layers. They're doing something good, which you would figure they would, since the VL model is able to, answer questions well. Anyway, I think that's enough for now. Do foundation models know geometry? No, they don't. Let's read that paper though. Okay, that's enough. We have lots of stuff. Let's see. This is a friend's paper. Unless they tell me that they're here, I'll just save their paper for last because I already know we're going to talk about it in more detail. I think we'll do the blog that I missed from last week first. And yeah, I think that's okay. So let's get, there's a column about LLM layers doing better. Send me the link if you want me to look at it. If you're allowed to send a link, does the automod filter links? If it filters links, give me a title and I can pull up the title. Anyway, let's try to jump into it. So view PDF, and then for the vertical, I need to change this. I need to pull up my timer. I am going to glance at my OBS just to make sure that we are looking good. We are. Probably do this part with the OBS in mind because occasionally I'll glance. Or actually, no, I'll just use the YouTube stream even though it's a bit delayed. Okay. 1 minute starting now. Okay, so geometry guided reinforcement learning for multi-view consistent 3D scene editing. Immediately I'm wondering why I opened this, because it's RL and it's 3D, which are both things that I don't know super well. So this is already a big close candidate, but it looks like the idea is that you take some input 3D, which you would gather with multiple cameras. So it's not like we start 2D, but then with the multiple cameras, or I guess feeding it to the model, maybe these look like we're taking our camera perspectives and actually we're getting just 2D views that we're passing in. I assume that M is number of cameras if we were to look. Yeah, viewpoints. So just the number of cameras. We add some prompt, which is the edit that we want to make. We pass to the RL3D edit model, and it does the 3D reconstruction to give us the edited 3D. The big pipeline there is this flux context, which generates a lot of samples, which we then feed to a bunch of frozen. Wait, did I not start the timer? Okay, that's a great goof for me to do in the first one. We'll fix that in the next one, but it looks like the fine-tuned flux context becomes this RL3D edit, which is able to turn all of my input 2D views and some edit into like a synthesized edited 3D. And it looks like it does that just by generating a ton of images. Like a ton of images. Oh, and it looks like it even has better 2D editing before and after this fine-tuning, which I guess makes sense. It's done a lot of fine-tuning on 3D consistent editing, so perhaps it should be better at that. Okay, I say we don't keep this, mainly because it's so far out of my expertise. I'm just going to say stupid stuff. So let's exit. Or actually, I'll leave it up just in case anybody wants to like save it. Wait, no, how will I keep track of that? Okay. I'm going to close it. If anyone loved it so much, they could say in the chat and I would open it back up. That's our strategy. Okay. So view PDF. See, I need a macro to do this. I was experimenting with the resize before the stream and I couldn't find a non-manual way. But anyway, 1 minute, let's go. Okay, train any agent simply by talking. So we take an OpenClaw agent and a bunch of general agents, or is this an either or kind of situation? It says train any agent. So maybe this is just whatever agents we want. We have some environment servers. We have an RL server with a training engine, a policy server, and a PRM. Oh, geez, this is getting outside my expertise as well. Lots of RL, lots of like super agent-specific stuff. It looks like the idea is that there can be binary rewards from conversations or on policy distillate we support, on policy distillation training and binary reward optimization. Some interactions can be good or bad, and they can give stepwise rewards across trajectories to try to make your personal open weight agent better, I guess. Okay, that's definitely a not keep angle for me, just because that's another one that is going to just make me look dumb. Like RL agents, way far from my wheelhouse. Penguin VL. Okay, this should be getting more into things that I can handle better in a minute. So let's go again. And maybe I shouldn't insult myself so much. It kind of ruins the mystique, right? Okay, so exploring efficiency in VLM with LLM-based vision encoders. So this part sounds really interesting to me. What do they mean by LLM-based vision encoder? So the image gets a random init image encoder or random init text encoder, contrastive training, that's lava style. Okay, cool. LLM supervision would be, we don't have a text encoder, we just pass text to the LLM and we have some kind of clip init encoder. Or theirs is we have the text LLM as the encoder initialization for the image and we supervise it with a feature reconstruction loss. Let's see if I can get another diagram for that. So the vision encoder is initialized with weights, and we use the 2D rope from the pre-trained LLM. Images are fed in native resolution, projected, text is tokenized. I think we got the gist of it. The main thing I want to see if I can answer in these final seconds is like, is this good? And the answer is, oh no, it's hard to see theirs. Right? Am I crazy? Oh, Penguin VL. So we should be looking at the left column. I mean, it seems good. This is interesting. I want to come back to this one. This is a keep for me. This for me is interesting. Oh, good question. Do you mainly review vision focused papers or also language ones? I am happy to do language by request. When I'm the one picking, I'm going to pick vision because it'll make me sound smarter than I am. I know enough to do some language papers. I'm really going to struggle like those first two papers we opened where like one of them was like really engineering heavy, RL and agents. I'm not going to have a lot of good stuff to say about that. The first one, if I spent more time, sure, could have been decent. But yeah, in general, when it's my taste, we're going to open a lot of vision papers. And lately, it's going to be a lot of video gen and video understanding papers and a lot of like big multimodal language model papers. But like I said, if there's a paper you like, just give me the title and we will at least spend a minute with it. I don't mind. Like a minute is totally fine. I think I did decent with that one. I don't know. Maybe I could have been a little faster once I got what it was. I kind of rambled a bit there. So let's try to focus up for this one. All right. So, oh, video streams into 3D. What do they mean? Oh, geez. This diagram is so difficult to not zoom in on. It looks like the gist is you can do a lot of different tasks. 3D object detection, 2D segmentation, depth, reconstruction mesh. There's grounding, there's spatial reasoning. Capable of converting raw video streams into holistic 3D. Oh, I hit the timer. That's going to be a tricky thing. Okay, let's pause the timer. Okay, I actually want to try this one again. I need to figure out what to do when the diagrams aren't awesome and or they're just like language or math heavy papers. I need to have like an answer to that. So let me like take a sip of water and give this paper its fair shot in the speed dating. Okay. So we need to figure out what they mean when they say they're taking video streams and turning it into 3D spatial intelligence. This diagram is a little tricky because it's not showing me the inputs they use to train the model. It seems to just be advertising tasks. So let's see if we can find like a good diagram that's okay. Step 1, geometric optimization. So our input is images. We pass those to call map. Oh, that makes it look like we need multi-view if we're getting high fidelity 3D structure for video streams using 3DGS. So we're going to need some multi-view and the camera parameters through the call map to get our 3D from video. So it's not quite what I thought because we're then just going to be able to use like a depth anything model to get like the point clouds. Yeah, I think they're relying on multi-camera video then. Or like a camera with multiple perspectives. I don't think this is like single view. Or maybe it is. Input RGB, SAM3, 3DGS rendered depth, object edge refinement, floater free, OBB extraction. Yeah, this one I totally failed to see what was going on in 1 minute. It's a revisit candidate, but I might not. 3D also is not, like I said, not my wheelhouse. So I might just fumble even longer if I spend even longer. Let's see how I do on a pure clustering paper. This could either be really easy to look at or really hard, which I know that's like a meaningless thing to say, but I just mean I know clustering. And like I know these libraries. Like I've used FAI, SS, or I say FACE. I don't know if anyone says that. But they're saying they outperform FACE by like 200 times, which sounds crazy. Which I think means that this is going to be like very engineering heavy. It looks like the gist of it is that they're going to stream blocks and then they're going to kind of mimic like things like flash attention to do, well, they're calling it flash assign, but basically they're going to tile the input to compute all of the similarities like gradually, and they're going to do maybe like kernel fusion operators to make it really, really fast. And I think that's the idea. Like, I think if we scroll to, I don't even know if there's going to be a numerical results table, because I think my understanding is that this does not change your like result at all. It can be deterministic just like any other k-means, is my broad understanding. Don't think I'll spend more time on this. It's more engineering heavy. I think it's pretty cool, but not necessarily the kind of idea that I'm trying to cover here. So we'll close that. Let's get to this guy. Long context geometric reconstruction with hybrid memory. So, okay, this is going to be another 3D one. But I was really curious what the memory part of it is. Do we get a feel for that here? Yes, kind of. So we have a chunked input. We treat the sliding window attention as a local memory, and then the global memory is a test time training thing. I think I understand what happens then with this test time training. Yes, it's like we have some kind of fast weight matrix, which we update with every autoregressive step. This is a common approach if you're familiar with test time training. And it looks like that's all this is really. Sliding window attention, fast weight matrix across chunks. And we can use that to do, it looks like a sweep like around a scene to learn to reconstruct the whole scene, basically. That seems pretty clever, pretty straightforward, and based on these numbers, it looks like it's really good compared to these baselines. You want a low score, and so they have generally pretty low scores. Okay, that was a cool one. Not my wheelhouse. I think I covered it good in 1 minute. Let's close it. And let's go next. Unified multimodal understanding and generation with masked discrete diffusion. Okay, I want to look at what's going on here. I'm actually going to skip right past the diagrams and try to see the tasks. Okay, so we've got some like visual question answering type tasks. And what else do we have? We have text to image, speech to image. Does that mean this model's processing audio like natively? Oh, cool. That's what it would seem to be, as it's natively processing the speech. That's kind of neat. Okay, so speech, image, text input, and then it can give interleave text, image, speech output. Okay, now we can look at like how it works more properly. Oh, no. Okay, it looks like, okay, I'm not sure if it actually takes the audio in or if it transcribes it. I don't know if it matters a lot either way, but you can take all those inputs, interleave them, and it can generate speech. Wait, do they have that result? Some speech generation? That'd be kind of cool. I'm not seeing the number. I kind of wish they had more tasks. And some of these are older benchmarks, but the results are competitive. It's kind of interesting. You see a lot of these papers these days. It's really hard to evaluate them when they don't have like a full spectrum of results. And I don't see anything crazy in this paper that makes me want to look at it for longer. So I think that's a close angle. Okay, one problem is whenever my timer goes off, it covers chat, which makes me like not see. But luckily, or maybe unluckily, nobody's chatting right now. So it doesn't matter anyway. Oh, one thing I've been forgetting to do, I don't think I have shorts viewers, but I've been forgetting to resize every paper, which means that these are like kind of useless for shorts for when I try to cut it later. Oh well, I remembered now. Okay, let's call all those practice then. I probably won't clip those, because at 100% it's like cutting off a big part of the margin for all the shorts. Okay, little break for my voice. And condition-aware routing of experts for contextual image editing. So I want to see the experts. These are cool results for instruction and subject-driven editing. Lots of kinds of editing. But yeah, what do they mean? So they can do instruction-based editing or subject-based editing just with the LoRa. That's prior works. Their work trains the LoRa on top of many different experts. A mask expert. Wait, what? What does this mean? Karen incorporates all these modalities in the user-defined mask with condition-aware routing of experts. Man, I'm not quite sure what they mean. Oh, okay. So it looks like we have a bunch of different encoders. Given multimodal conditions, inputs are tokenized and projected to heterogeneous expert branches. Then the router, which is learned, will assign a confidence and select the top K experts to process each token. Expert outputs are normalized, fused, and then through the latent model where the LoRa acts on top of the weights so that it can handle the new latents. And yeah, that's how they do many different kinds of editing. I want to look more at this one. I don't think I quite got exactly what they do. I think it looks interesting enough. We will keep it. I'll also go back to these real quick and change the size so that I don't forget. Bummer that I didn't remember to do it earlier. Oh, I said I would do this first, didn't I? And then I forgot. Let's take care of it real quick then. Yeah, let's do that. All right, did I close my timer? Oh no. Okay, hold on. It's so annoying that my instinct is just to close it. No, I don't want to do a focus session. No, I don't want to focus. I just want a timer. Okay, boom. Timer is back, and we are back. We are so back. This is a paper I didn't get last week, by the way, because it's not a paper. It's a blog. I think it's cool, though. And so, building native multimodal unified models end-to-end. They have this native vision language model, which can take a patch embedding or a word embedding or interleaved noisy patch embeddings. What's the deal? Why is this one noisy? Is this for when, do they do understanding when they take the clean, but then you can feed it noisy and like natively denoise the tokens? Is that what they're saying is happening there? That is a little unclear. Based on the tasks though, these are a lot of different visual question answering tasks, so it's a good understanding model. You can see here they don't overlap a ton of metrics with Bagel, which is unfortunate, but in general, these are pretty solid multimodal numbers, both at the 2B and 8B scale, and it has a lot of 2025 models at least. So my initial impression, especially looking at these qualitative, is that this model is quite strong. And so I think this is going to be missing some like algorithm details, I guess. So I think we've covered about as many of the details as it has, but end of the day, interleaved image text input, interleaved image text output. They're calling it the first end-to-end, which might mean that I passed the 1 minute mark, but I'm not going to revisit this more. So I'm just finishing what I want to say now. I believe that what they're saying is that they don't have like a visual encoder on the patch input, just a lightweight like encoding. That's what they're calling it end-to-end. Yeah, no VE, no VAE. So that's the main idea. You can do the reconstruction without a VAE decoder. You can do the semantic input without a VIT encoder. That's pretty cool, and those results are awesome. Okay, next. I don't really understand actually how they did it. I don't think the blog doesn't really say either though. I mean, the gist of it is just it works, which is what you get sometimes with those blogs here. Sorry, I minimized the tab. Okay, so let's open next. View PDF. 85%. Pull up my timer. Sip of water. I wanted to see this new intern VL model, democratizing unified multimodal models. So this is more unified multimodal. So we're going to get really pretty image gen results like we've been seeing in a lot of these. What I really would like to see is a diagram, and if we can understand any of the interesting things that they do just from the diagram. So they use a text tokenizer, and they use a visual understanding encoder, and they use a visual generative head. So very different from the last one we looked at. In fact, if anything, they go even, okay, and they're doing velocity prediction. So this is like a flow matching or a diffusion-based decoding, which is pretty common. The other one was the outlier. This is a very standard workflow these days. Let's see if I can tell the interesting part. So the visual generation head has dual stream attention, dual stream FFN. That's kind of interesting. It's not single stream, it's dual stream. So that describes how we're processing the image latent versus the text latent, or versus whatever the context latent is. And you can see how that works in the diagrams here. Not that that's new. I mean, that's just a choice made on existing architecture. So my first guess would be that the really interesting thing here happening is data. And actually, that is true. Okay, I'm going to revisit this one because I'm very curious about the figure on our screen now. But I'll move on. Because I think the secret sauce is the data, and more specifically, it looks like they do something with synthetic data. That's interesting. Okay. I promise, I know that it's a bit rough now. I swear I'm going to get better at this as we go and actually say more of the useful things in the 1 minute. That's the goal. Maybe I'll need to increase it to 2 minutes. But let's see, I don't know. Okay, I've been excited for this one. So a compact discrete tokenizer for latent world model, planning in 8 tokens. I think it's, okay, I just nuked everything. That's like a fidget. Sorry, let me reset. Oops. Sorry, my instinct when I see these diagrams is to full screen them, but we're trying to make this shorts friendly, so we're not full screening. Let's try again. A compact discrete tokenizer for latent world model. So when we look here, we see that their tokenizer training is just your standard encoder decoder type of training. Their latent world model training encodes, masks, and then predicts the unmasked. Oh, that's different from what I thought. So the latent world model is trained to model the conditional distribution of the future state where we adopt masked generative modeling. Wow. And at test time, the learned latent world model is used for decision time planning to minimize the distance between the predicted final state and some goal image. So it looks like we'll make a series of predictions from the input, and then we want to predict something that matches some future output in the video. And the tokenizer architecture detail is a VQ-GAN as a target latent, a DynaV3 with a latent resampler to try to match, I believe, that VQ-GAN target latent and then decode with the VQ-GAN. We're going to need to come back to this later because I'm not quite getting it quickly enough. Oh, and they have an even more compact variation. Okay, cool. I think I hit the main points. I think I just said them, though. I didn't, like, explain them, which maybe I'm running into a barrier with how this format works, but I really hope I'm not. I would like to get to where I can just look at a paper, know the best thing to say in 1 minute. But who knows? Maybe the learning from this will be that a 1 minute summary is a lot better after a paper than before you read it. We'll see, though. Video-based reward modeling for computer use agents. So I'm curious if they show, this should have a diagram, right? Okay, so we get a video trajectory from a user task, feed it to the vision language model, negative, wait, what the heck? Oh, they synthesize negative samples via adversarial instruction translation. So, what? They have a training data set, they freeze a vision code and projector, then code video frames into patch tokens. Token kept only if, no, I'm not. Yeah, not enough visual here, and there's 3 algorithms. This one's going to be a really tricky one. Maybe I can save myself on the abstract a little bit. Video task reward triplets, and adversarial instruction translation to synthesize negative samples of step-level annotations. So it looks like they're going to use the video densely based on this diagram in order to generate like slightly different things that end up diverging from the regular task flow. So they have users do tasks right, and then they have a model generate what it would have looked like if they did it a little wrong. Okay, we're closing that one though, because not in my wheelhouse, and I'm not really interested. I think we did Wild Actor last time, but I'm going to try to speed date it. If anything, this should mean I'm even better at going over it in a minute, right? We've looked at it before. So let's do 85%. So the idea here is unconstrained identity preserving video generation. We have all of these references, and we want to generate that person doing anything it looks like. It looks like our references don't necessarily give background. Do we give, oh, there's an original video straight up, or is this just a pipeline for how they construct the data set? Yes, we're generating data sets by cropping faces and bodies, and then by sampling for diverse viewpoints. We're just making data sets. Is that what this paper is? Is this mainly a data gen paper? Or no, once we have the references, that's right. Once we have the references, we sample them, we pass faces and bodies and the input video to the 3D VA encoder. We pass all of those tokens. We limit the attention to where everything attends to video tokens, but video, like face and body, don't attend to each other. And we do LoRa on top of the DIT to learn how to do this identity preserving video generation. I think that's a pretty good summary. I am 99% sure we did this last stream, so we will close it here. And I will drink water because I'm like, my throat's hurting a little bit. The whole 1 minute thing does not leave a lot of time to like breathe air or do anything other than kind of hurt my vocal cords. Okay, I was excited for this one because we're doing some kind of hierarchical denoising for the long video. Efficient autoregressive long video generation via hierarchical denoising. In this paper, my guess is that it's going to kind of resemble pyramid flow. This does not tell me a lot. They just said their model's good, right? It's got good continuity and good quality, and it's got like any length. Let's look at how they do it. So the hierarchical denoising performs causal generation across all blocks, conditioning on context to all the matched noise to suppress error accumulation. I'm not seeing the part that like spells out to me immediately how it's hierarchical. Conditioning on context at the matched noise level. Oh, I suppose that the context isn't. It's kind of like diffusion forcing. So like they're saying that when they're denoising the early steps of some new frame, it's conditioned not on like the latest clean, but like on the latest noisy, I think is the main idea here. And that makes sense. So I bet they're going to compare against like self-forcing, causal forcing, pyramid flow, like I said. Okay, that makes sense. I want to look at this one just a little more later. I think my guesses were good. Maybe that's a good thing I can do. I can guess and I can be right. That is a fun way to generate a minute of content about a video. Omni motion controlled multi-subject video customization with latent identity reinforcement learning. So we're trying to control the motion with multiple subjects, customize the video. Let's see how they're doing that. So it looks like we're going to draw some motion control and provide, okay, what? Draw for motions, boxes for camera, and we can provide the subjects and give like the relative placement of the subjects and then what we want them to do. That's what it looks like to me. We're going to train it with encoded videos, bounding boxes, subject references, prompts, hand trajectories, which are kind of like hand drawn. And then those all need to match whatever came from the input video. Then the whole latent identity reinforcement learning part says that our model generates these features. Like we take features from the diffusion model. After cross attention, after a learnable head, we compute a reward according to some preference labels. Where the preference labels are gathered from human preference? Is that the idea? I would assume. Or they're generated automatically? That's the one question I have. I think that's a decent minute, and I think I'll come back to this one. I think I gave a good high level of what it does, though. I don't know. What do you guys think? How's this going so far? It feels a little weird in some ways. I don't know. Also, but when you said SLA2 forever ago, sorry, I didn't notice that. Did you mean a paper called SLA2, or what were you hoping for with that? Anyway. One model, many budgets. Oh, I shouldn't read until I've got the thing going. Elastic latent interfaces for diffusion transformers. I want to know what elastic means. I think it means we can make the latent bigger or smaller, but I don't know. So it looks like we extend a DIT like generator with the variable length. The length of the set of latent tokens can vary, and lightweight read write. So how can I really tell how it's varying? Group replication, tail dropping. Oh, so like sometimes we'll use the full length, sometimes we won't. But no, it's a variable length set of tokens. So like it's a variable number of tokens. But the tokens typically have this like forced spatial correspondence. So how exactly is that working? How much faster is it? Does it work? Compared to DITXL, the FID is worse, but no. MB is their method, right? So I'm a little confused. I'm intrigued. We'll come back to it. I wish I could have read that table in time. I almost had a really good minute. Sorry, I know I'm treating this more like a challenge for me almost than educational. Hopefully that starts to flip as I just get good at the hard part. We'll see. Okay, adaptive length video tokenization. So in what sense are they adapting the length? That's the thing we're going to try to figure out here. So they have a proxy tokenizer, which is trainable to reconstruct videos under all candidate assignments. And then they apply the proxy tokenizer to compute proxy rewards for all candidate assignments across videos from a data set. To curate a data set of videos and their optimal assignments. Then they train a router to predict the optimal assignments. Then a final tokenizer trained from scratch. Oh, so they train a tokenizer that can give like variable length tokenizations. And then they just perform a matching, which basically says when does a video need a long one versus a short one. And then they train another model that can detect given a video where to route it. I guess the tricky thing is how do you tokenize things for the router, right? Because here's the variable length video tokenizer itself. But where's the architecture of this router guy? Like, what is the router? I want to come back to this and answer that what is the router question. A minute 30 is a decent idea. It might mess with me trimming for shorts, but it'll make it so much better that, yeah, I think I agree with you. That's a good idea. Let me give myself a 3-minute timer, or sorry, a minute 30-second timer. And yeah, let's try to spend that extra 30 seconds to actually like skim the abstract. That's the big change we'll make. I think if we skim the abstract, we give ourselves a much better chance here at really like knowing what the paper wants to tell us, because sometimes I'm spending time not just like trying to find the thing in the paper. I think I have been getting better at figuring out the question I want to answer about the paper, but this whole abstract thing is going to give me like a little cushion. So that's a great idea from Stochastic XYZ. Examine your zipper. That's what I think of with XYZ. Is that from The Office or where, or is that from How I Met Your Mother or something? I can't remember. Anyway, mastering perception, reconstruction, action, and continuous streams. So it's a unified. See, that's the problem. If I highlight stuff, my timer goes away. Okay, starting again. But that's kind of confounding. Maybe I need like a, I don't know. I don't know what the solution is to that. I'll play around with ideas off stream. I need to do something about this timer. Maybe I stop using the Windows timer and I have a different app that just like kind of floats and looks prettier. I don't know. Mastering perception, reconstruction, and action in continuous streams. So they have a unified streaming visual backbone that's going to do all these different tasks with visual inputs. They're pre-training it with a multitask framework that couples temporal and static representation learning, which means they're doing both like image and video, geometric reconstruction, and vision language alignment on 29 data sets. And they show even with the frozen backbone, it achieves competitive performance of specialized experts across image video probing, geometric reconstruction, and lots of complex tasks. Let's look a little more about how they do that. So I think this just shows the tasks they support: perception, reconstruction, understanding, and robotics. And you can see like their radar plot. Okay, the overall framework. We can take image, video stream, or 3D scene. We need to embed them. We need to feed them. Okay, so we're using 3D rope for the tokens. That makes sense. And some causal spatiotemporal. Yeah, that makes sense. Just like 3D causal attention. We're getting out a class token, a camera token, and we're feeding all of this stuff to a network that's going to compute the temporal reconstruction, which is going to be distilled from some teacher network, and all this geometric data, which we can get either ground truth or use experts to compute, I imagine, and then vision language based on some caption, I guess, that we also have as input. And then the results are going to be diverse depending on the task that we are comparing for, but like kind of competitive across the board. I like this. We'll come back to it. The thing that I missed that I wanted to get is what about this is streaming as opposed to just image or video? Streaming would normally imply like I'm going to have an infinitely long sequence, and I missed where they're handling like memory or test time training or something that would allow them to account for that. So that's what we're going to try to hit on the longer pass. So some of these longer passes might be like 5-minute passes, you know, because some of these things I've said, I really just have the one question, you know, and we can answer the question and then we're good to go. Ooh, I can change my cropping, I think I'm realizing, because I'm looking at my stream preview and I think it's already trying to be a little smart, maybe. I'll keep that in mind for next time. Anyway, identity-driven audio-video personalization with in-context LoRa. I don't think there's going to be much to this one, but maybe there is. I think it's just going to be like a LoRa for whatever the identities are, and we just need a decent number of like references. But let's see. So they have an LTX joint audio video backbone. Two challenges are reference and generation tokens share the same positional encoding, make them hard to distinguish. So they have negative temporal positions, which place the reference like outside the frame of the video. That makes sense. And then speaker characteristics are diluted during denoising, so they introduce identity guidance, which is some CFG, which like makes the speaker more important. Okay. And then the ID LoRa, okay, so then their method is good is what they're saying. Okay, so they have the reference audio, they have the first frame, they have the prompt, and then they're able to generate, you know, a whole video with the audio in the first frame, like personalized via their ID LoRa, which based on what they said about the training, one key thing is the context is all placed at like negative positional encoding, and then the target happens in like positive space. We're going to use an audio VA and a video VAE and train a little LoRa on top of the LTX2. I think the main point of the ID LoRa is the identity preservation. I wish I had more detail in this diagram about how that's happening. Very hard to comment on that otherwise. It looks like they encode it into audio latents, but no, that's just the audio encoding, like generically. So where is the identity preservation part of it? Identity guidance, classify for guidance that steers towards, okay. Man, so close. I think if I did that a little better, I should have realized looking at like reference conditioning, we already knew what that was. Like that's literally just passing the image as the context. We already knew about negative temporal position. I should have immediately gone to the identity guided inference and we could have got that in the minute 30. I think that's very doable. I don't want to come back to this one, so I'll just look at that now and pretend I got to it before. So the way that the identity free guidance works, there's an identity guidance scale, which is going to, basically like, a forward pass with the reference conditioning and without, and then take the difference. That's cool. That's a clever little manipulation. I don't know if it's novel, to be clear. Really hard to comment on that. There's so many papers. The pace of research is crazy. But yeah, the gist of it is they're going to do a forward pass like with the reference context and then one without, and they'll take the difference and they'll say the difference between the forward pass with the reference and without the reference is essentially the reference itself. And so once you have that, it's kind of like a slider and you can turn up the weight of the reference and that gives you the, sorry, why is this taking me so long? And then that gives you like fine-grained control over the strength of the reference. And so basically once you've tuned your LoRa, hopefully there's a value that tends to work good. Isn't that just CFG? Like, yeah, it's just CFG, but like, is it actually just CFG? Like, is it literally just CFG? I guess that's literally just CFG. I think the difference between that and the CFG is it still has the reference audio, right? Or are they both withheld? So I thought it was like a little more granular because it's like even our unconditional has the reference audio. Yeah, I think it's literally CFG. I'm just saying I think using it specifically because like the thing with the reference context is the reference context isn't a condition, it's part of the sequence. That's why I'm saying I don't see it just as CFG. Like, I don't know, maybe this is stupid because there are a lot of newer models where the condition is always part of the input, but I guess I'm thinking of like traditional DIT at least where your condition is something that you just use in like your add a layer norm, right? It's not something that's actually an input to the model. It's just continuously injected into the model. So I think that's why I see it as a little different. But yeah, no, there are models that always take the condition just part of the stream. So this is, in that sense, this is just totally regular CFG, except they're saying it lets you control the identity because that's what the condition is in the case of this LoRa. So fair point, Sam's Li8TJ. It really is just CFG, I guess. Okay, next. Okay, the one thing I have to find a solution for these streams is my throat gets kind of itchy, like almost immediately. Maybe I need like some really nice tea or something in order to help like survive. Okay. Streaming autoregressive video generation via diagonal distillation. I know what streaming is. I want to know what diagonal distillation is, which operates orthogonally to existing approaches and better exploits temporal information across both video chunks and denoising steps. Central approach is an asymmetric generation strategy. More steps early, fewer steps later. Okay, that's not too crazy. This design allows layer chunks to inherit rich appearance by aligning the implicit. Okay, there's nothing diagonal about that yet. I mean, I'm not saying the method's not diagonal. Let's see it. Okay, so, that's what they mean. Cool. So in earlier steps, we get like this idea of what the video is, and then we have like a nice video in context, and then we can rely on that and use fewer steps. And this, I think, describes inference, right? Yeah, gradually reducing them by chunk 7. I think this describes inference. They're talking about a distillation framework. Unfortunately, it looks like we're mainly going to have to actually read the okay, let's try. Core innovation diagonally denoising, that was computation based on the method assigns more denoising steps to earlier chunks. How do we train? How do we train? How do we train? Where's a loss? Two-step, no, I don't see L. Give me an L. Loss, DMD, distribution matching distillation framework. Nope, that's the standard one. What's yours? The distribution matching plus an LReg plus like a gamma weight and alpha weighted combination of both. What? man, I would need, getting the method specific thing out of this text is really tricky. Something I'd like to be able to do. Maybe if I had like an AI tool in here with me, it could read it while I'm talking, and then it could tell me what part to look at. Maybe that's the strat. But I like this. Even without knowing how they train it, I think this is an interesting idea. I'm very curious how well it works without even doing the training. And that's what we'll look at later. For now, let's open another PDF. We are almost at the end of the Hugging Face. So that's pretty cool. Good for us. Training means taming mean flows for one-dimensional causal image tokenization. Okay. Autoregressive language models rely on causal tokenization, but extending this to vision remains non-trivial. Currently, we flatten 2D patches into non-causal sequences to enforce heuristic orderings. That's true. It's kind of weird, like saying that the first token on the upper left is very close to the token to its right, but not as close to the token below, would be a weird thing to imply. Okay. So to address these, they present a causal image tokenizer with mean flow decoder. By selecting tokens over time intervals and binding them to the mean flow, they learn to make a causal 1D. Okay, so they're basically saying we're going to make that 1D actually make sense and have causality somehow. By taking tokens and then doing like a filtering and selection that basically says what the order should be, I think is what I'm seeing. Okay, so we have a causal VIT where we take image patches and registers is a detail you can just ignore. Those have image features. Oh wait, it's not necessarily because the registers turn into the 1D tokens. Whoa. So we get the register tokens of the VIT. We select on those to the mean flow VIT. We feed in the noised images. Oh, so a causal vision transformer encoder gives us registers that are the 1D tokens. And then these are conditioned to the decoder through time interval selecting. And then the two flow objectives and two representation objectives allow it to learn causal 1D representations that support both one-step and multi-step sampling. Are the results good? Decent. Decent. And they compare to RIPA or SIT, and it looks decent. Oh, they don't compare it to RIPA. They use RIPA or don't use RIPA. Dang, I wish I had said that right during the 1.5 minutes. This is cool. I think I got it in a minute and a half pretty good though. So we have a lot of papers, so sometimes I just need to say good enough, even though I did like that one. Wait, did we already hit this one? Yeah, we did. Okay. A programmatically verified benchmark for visually grounded deep compositional reasoning. Okay, how do we do the programmatic verification? Visually grounded deep compositional reasoning. Each benchmark is organized as a multi-layer reasoning chain where every layer retains non-trivial compositional condition. So the LLM must perceive the image in detail, reason over multiple elements, and follow the resulting execution path to the final outcome. They propose an agentic synthesis pipeline. A planner orchestrates layer by layer generation of compositional conditions. And then a verifiable programmatic or immediate representation ensures every layer's condition is mechanically verifiable. Dang, this is such a... I would need to zoom in order to see what happens with this, which would be bad for our friends. And do I have anyone in vertical, by the way? You can comment. I'm very curious if there are any shorts vertical viewers right now. Yeah, I don't know. I'm not inclined to speed date stuff that you can't read any. Like, I have this on my screen at 8.5 by 11, by the way. Like, if I hold up a piece of paper, this is like, yeah, and I can't read it. So that's a next. I hope it's a good paper, but like at some point the entertainment in the stream is as important as the education, and like I have some constraints. Okay, video LLMs can watch and think simultaneously. What do they mean by this? So online video language models focus on streaming perception, lacking logical reasoning. Fair enough. Mainly they just encode, and then whenever there's a question, you'll like pull the stuff in the cache and try to answer. So it's not like you're reasoning in real time. However, directly applying test time scaling makes it really expensive. They're slow enough as it is. So we have a novel paradigm to think while watching. So what does it do? We introduce a comprehensive post-training pipeline that integrates VST SFT, which structurally helps it to do causal streaming reasoning. Additionally, okay, so what they mean is you can take a video clip plus query, and the online model give an answer. For an offline, it's just video plus query, give an answer. Okay, these are things we know. But for theirs, we can take a video clip and save a thought, and take another video clip, save a thought. And then we're always taking the thought in as input. That makes sense. So instead of just encoding till the moment we get a query, we always save that output or even give an output, and that's like a thought. So I think this is text-based thinking, right? Yeah, we're taking our thought in text. So I would compare this to, this is essentially a text-based memory more than it is a reasoning pipeline. It's reasoning in the sense that we pass text through the model multiple times, but in some sense, the purpose of the text you pass through is mainly to remember what happened, right? Like the video opens with a $1 boat, immediately followed by a jump to a $1 million yacht. Like that's just telling us the history. Okay. Language-based video memory. Cool, but there's a ton of those. So that is a good close angle. Did I close it? Yeah, I did. All right, next. Spatial test time training. Okay. Streaming-based visual spatial intelligence with test time training. So humans perceive as a stream of visual observations, and they reason and understand in the same way. So they want to do streaming-based visual spatial intelligence to capture, specifically, they design a hybrid architecture to adopt large chunk updates parallel with sliding window. Okay, so it's kind of like the paper we looked at earlier, sliding window attention plus some kind of fast wait updates. To promote spatial awareness, they introduced a spatial predictive mechanism applied to the TTT layers with a 3D spatiotemporal convolution to try to capture geometric correspondence as well as the continuity across time. Okay, do we see the architecture here? Man, it's hard to see that architecture. It is really hard to read that architecture. Let's hope they have a better diagram here, maybe. So the model employs a hybrid architecture that leaves TTT layers of self-attention anchor layers at a 3-to-1 ratio to preserve the pre-trained knowledge. Okay, so I think they meant a 1-to-3 ratio, no? Or is it really a 3-to-1? It looks like 1-to-3 for real. We just have a ton of these test time training layers, which have the sliding window attention, the TTT operating in parallel with the shared KV projections and the fast wait updates, like I said from before. Where at each step in the autoregressive generation, we're making some update to the fast waits, which we can concatenate to the sliding window result to have this effect where like we're always looking across the whole video at things that are like recent, but we're also maintaining this fast wait, this like longer context thing that's updating across the whole video that we process. So I guess the main contribution here is this ratio, I'd say, that they propose. I'm not going to spend more time on that one. Deterministic video depth estimation with generative priors. They repurpose, okay, so they have 3 core designs. They repurpose the diffusion time step as a structural anchor to balance global stability with high frequency details. That just sounds like step rebalancing probably. They have latent manifold rectification to mitigate regression-induced oversmoothing. Oh, I'm interested to see how they do that. And then global affine coherence to bound the inter-window divergence to enable seamless long video inference without requiring complex temporal alignment. Okay, so let's see if we can find the diagrams that show how they do each of those. These just show results. The results look cool. Okay, the overview is on the top, the video DIT performs a single pass depth regression where it's been trained as a one-step regressor to go from RGB latents to depth latents to allow depth manifold reconstruction. For long video depth estimation, overlapping windows are seamlessly aligned using a closed form least squares solver. Oh, interesting. Leveraging the model's global affine coherence. So that's what they were talking about before, where they're going to predict overlapping chunks, which give them like these anchor points that they can use to compute the alignment in a least squares way that's probably similar to classical computer vision techniques. That time step as a structural anchor, these are just results. This is like some analysis of how the cosine similarity matrix, the time step embeddings, while embeddings are broadly consistent, mid-range time steps exhibit high similarity with a wide range of states. These are like nitty-gritty details. I was hoping for a better like diagram summarization of some of these, the 3 parts of their method. Not really getting that here. Do I want to come back to this later? No, I don't. Not in the mood. Okay. ByGain, unified token compression for joint generation and classification. So I think I already know what I want to look for here. What do they do? So do they take pre-trained tokens from what? So a Laplacian filter is applied to hidden state tokens to compute the local frequency, and the lowest scoring token is selected as a destination token, while the others, that is not a complete sentence. Sorry, it is. While the others form the source set. Destination source tokens are gathered globally, and a bipartite matching selects top source destination pairs. And so we use that to have like training data, and then we learn the mapping, or what's the main idea here? Is this training free? Yeah, it is. If I skimmed the abstract like I said it would, I would know that. Training free plug and play framework that, wow, that's interesting. So they do the token merging into like the lowest scoring token based on the local frequency scores. And then they interpolate, extrapolate key value downsample with downsamples key values via a controllable extrapolation between nearest and average pooling while keeping the queries intact. So it's got, they say good speed accuracy trade-offs. Let's look at the numbers. They can reduce the flops by 14.2%, which in the token merging space, that's this top method, is good, and get way better accuracy. Wow. As well as really solid FID compared to the prior works as well. We'll come back to this one for a longer dive. I think this is interesting, using the frequency data to basically determine which tokens you merge. Pretty cool. Let's come back to it. Let's look at this one now. Oh man, I forgot to do the resize for that one. Oops. Does AI see art like historians? What's their answer? What visual concepts do VLMs rely on when predicting artistic style? Do these concepts reflect criteria that art historians use? What kind of misalignment is there between VLMs and art historians? Do they give like clean answers to this? Wouldn't that be nice? They define the research question. Okay, we demonstrate the further, dang it. Okay, sorry, I was hoping I could find a place that would quickly give me their punchy answer, but I'm not getting that. Let's see if a figure is, okay, so this is the concept decomposition pipeline. They did image patching, and then, okay, so they split training images, extract the VLM latent representations, decompose them to obtain patch level concept activations, then generate text labels describing the top activating images of each concept. This is related to a lot of older work that tried to do similar things. What I'm really curious about is where they say if it lines up with the art historians. That's what I came to this paper for. Where's the art historian data? Am I just being dumb in how I'm reading this? Probably. They probably did it fine. This answer's probably, oh, here we go. The scores given for coherence on a scale of maybe 0 to 100. Here, that finishes the speed date, but I don't want to come back to this, and I kind of just want to know the answer. So we collect a majority label for each concept to report our results regarding inter-entity agreement. Figure 9 shows the distribution of scores. 93 received a majority score of 3 or higher, indicating the majority concepts do represent a single coherent art historical concept. Oh! So, oh, the coherence scores are 1 to 5. Oh, man. If I just read that wrong. Okay. So, a good amount of art historians, like a good amount of the concepts are reasonably coherent to art historians. I guess that's good to know. I think that kind of paper is perfect for the speed date if I didn't just totally fumble it, right? Because we went into it wanting to know one thing, and the one thing is learnable within 1.5 minutes. I just need to get better at the presentation of it and at like figuring that out in real time. From semantics to pixels, coarse-to-fine masked autoencoders for hierarchical visual understanding. Okay, so self-supervised visual pre-training methods. So yeah, contrastive learning, global semantics, MIM, models textures, pixels, but then has the attention drift. So they propose a coarse-to-fine MIM, which is going to resolve the tension by learning hierarchical visual representation. Okay, so what they're saying is that like all the different methods go from like low level to high level if you look at their attention maps. Their goal is to effectively capture features across all levels, because I think they're saying that the dyno always skews high level, the MAE always skews low level, the multi-MAE doesn't fix this, whereas they have some low level, some high level. How do they do this? So they have multi-granular data. They have RGB, semantic, and instance, which they mask by a progressive masking strategy and then concatenate and feed forward into transformer encoder, which are subsequently fed into a cascaded decoder with 3 task-specific blocks, one for each of these input tasks. Each block is a standard transformer decoder block with self-attention, cross-attention, feed forward. They use linear layers as the final predictor, and the masking strategy transitions from semantic guided to instance guided and finally to random masking to build a hierarchical visual representation. Okay, cool. I don't really want to know in this thing what each of those mean. We'll cover that more when we look at it in depth later. Does this work? 84.4 fine-tuning, which is a little bit better than the MAE at the comparable. Yeah, like a little bit. I'm curious if they do linear probe. Fine-tuning's kind of out of favor these days. So we'll look later. Okay, that was decent. This is really in my wheelhouse, though, in terms of things I know, right? Like I've done a lot of representation learning. So those are the papers I should be able to summarize in 1 minute and 30 seconds. If I knew these other areas that well, maybe the rest would be equally smooth. Anyway, okay, I need to rest my voice for a second. 6 more to go. What do you guys think? Chat's a little slow. Not the biggest deal. I'm not trying to say everybody has to stay stuff. I'm just curious if there's any thoughts. And I know a couple of you kind of alluded to having papers in mind, but I don't see any titles linked. One of you mentioned a COLM, a conference on language models, 2025 paper. You could send me the title. We could get that done before the speed dating ends. Or whatever SLA2 was, maybe. I'm not sure. Yeah, I'd be happy to look at those. Anyway, deep breath and stretch. Okay, let's do this. Modeling visual state transitions for consistent video retrieval. As video content creation shifts towards long-form narratives, composing short clips into coherent storylines becomes increasingly important. I talked about this last stream actually a lot. They formalize consistent video retrieval and introduce a diagnostic. By predicting a state transition residual update from visual history, they introduce inductive bias for latent space evolution, which they show that they they improve the performance for the retrieval. Somehow, I don't understand. This sounded like I'm not quite sure how the first sentence relates to retrieval is what I'm getting at. Anyway, so we have an input context and query. Standard retrieval often returns semantically relevant but temporally incoherent clips. Oh, that's what they're saying. Whereas they want to retrieve plausible continuation and re-rank the generation candidates towards more coherent continuations. I guess they're saying they'll avoid like jumps in the retrieval when you're retrieving multiple segments. Like when your clip does not follow the entire storyline, your storyline has to return multiple clips to answer that, I suppose. But I'm not sure. That's not necessarily what I see here. What's the method? Oh, this is the benchmark protocol. State negatives, temporally misaligned clips in the same video, and identity negatives, appearance misaligned clips to diagnose consistency failures beyond semantic matching. Okay, I'm not quite... And their adapter, this is just like a special attention mechanism. I'm not quite seeing the special part of this jump off the page at me. Like, and I'm also... That was a really bad speed date. I'm also not interested in going further. Sometimes that happens in real life speed dating, you know? Like, if the conversation's bad, that doesn't necessarily mean you're bad. I'm also not saying the paper's bad. Just maybe we're not a good fit for each other. That's what I'm trying to say. Just not my cup of tea. Oh, geez. This one took forever to load. I wonder why. Okay, thank you for the paper. Visual representations inside the language model. Cool. Yep. Ben Lin Liu. Cool. Yeah, we'll do that before this scan one, actually. Here, we'll do that real quick. Speed date time from a language paper. We don't yet understand why MLMs struggle on perception-heavy tasks. They study how popular MLMs process their visual key token value tokens. They study the flow of visual information through the language model. They reveal it correlates with the MLM perception capability. Oh man, these are a lot of findings. This is pretty dense for the speed date. Okay. So they study the visual representations in the key value cache themselves as they are uninfluenced by text. Okay, duh. And directly contribute to the MLM output. Despite elements struggling on perception, we find that their intermediate image value tokens encode sufficient information. Yeah, for very zero-shot perception tasks, calling for research to understand and surface the visual information they already present with MLMs. I think this is a great point. Like, it's basically saying that you can look inside the MLM, go into the KV cache, and actually get out, like, classes, segmentation masks, correspondences, and stuff like that. So, like, clearly there's good information there, but yet somehow the model still isn't using those well. Like, if the SIGLIP segmentation without MLM fine-tune is competitive with like a post-projection visual encoder for some of these complex tasks. Yeah, cool idea. I don't think we'll spend longer on it. This is also a cool visualization for the maps of keys and shows how they are like interesting visual features. And yeah, it is interesting to think, you know, if you have good features in your model, in your MLM, and it has such powerful attention mechanisms, I would say naively you could ask, well, why is it struggling to use that information effectively? Maybe the answer is it's still too much of a language model. And it's very hard to interface between the ideas that it has, which are in these text tokens, and the dense visual information that's in those visual tokens. I don't know. Visual explanations of self-confidence and analysis networks. Okay, so explainable AI. That's the type of paper this is. We're going to try to explain what these models are doing. So it's difficult to compare the explanatory power across models such as CNNs and transformers. They introduce a universal framework which can compare both CNNs and transformers. That's pretty cool. An autoencoder-based approach to reconstruct features from a model's intermediate layers, which demonstrate that it consistently does well on these quantitative metrics and produces clearer object-focused explanations. Cool. This is always a little scary because you're saying like, oh, the explanation's clear. Well, what if what the model's doing isn't clear, right? So maybe we're forcing the model to explain something and we're kind of accidentally manipulating the explanation to explain something that the model isn't exactly doing. But I like this general idea, which is that we can extract feature maps from the target model and then reconstruct them, and then the important regions which contain the significant information can be visualized with a self-confidence map. This diagram's not really doing it for me, though. I imagined like a very clear encoder decoder on features, and that's not what I'm seeing in the diagrams. I think I understood it fine, though. I kind of want to come back to it to get... Anyway, let's look at the results. So yeah, they're saying that we can do a better job of showing you what the model's looking at than the earlier models. Like this is what they say, this is what this model is, this is what the Resonant 50 V2 looks at. This is what the VIT B16 looks at. They have metrics too to argue that this is good. They compute area under the curve scores for the layer cam and the scan across weight randomized and label randomized settings to verify the fidelity of their target model. So these are the kind of things you'll see in papers that do things like GradCam. And it's cool, a framework that's agnostic to both, because like GradCam is CNN specific, all this like attention deep dive stuff is obviously transformer specific. So it's neat to get something that's agnostic. I kind of don't want to come back to this paper, so I really just want to understand exactly what the encoder decoder thing we're doing is. We take feature maps. Oh, maybe these are supposed to be, no. I guess these are supposed to be feature maps from the target model. Where's the, and reconstructed, what? Maybe my mistake is that there's not a model doing the reconstruction. I might be like forcing myself to misunderstand what's happening here. No, it says autoencoder-based approach to reconstruct features. Generates a high-resolution self-confidence map. Yeah, I'm gonna call it on that one. I don't think I'm going to... I need to come up with a quick way to tell you guys, like, I just don't think I'm going to get something that's good for the stream by just staring at the paper longer, which is going to be the case with some of these papers where it's a decent paper. I'm not like an idiot. Maybe I am. But I think some of these, like, the information density is such that the stream gets real boring. And I kind of hate that because it almost pushes us more towards vision papers to some extent, but I don't think it has to. Like if some of these methods sections are tagged, well, we can find key equations within the speed date time even. I don't know though. Something to keep thinking about. Multimodal large language models as image classifiers. So okay. Multimodal large language model classification performance critically depends on evaluation protocol and ground truth quality. Our multimodal reannotation of a bunch of classes reveals that MLMs benefit most from corrected labels. Oh, interesting. So they're saying that a lot of the mistakes that MLMs make with images are just places where the image data set's wrong. And then finally, they show that LLMs can assist human annotators. Okay. Yeah, I think I'll fill them in it. No, I'm not interested. It's a fine idea. Like, okay, the ground truth is mislabeled and the MLLM is so good it's punished for that, but I'm not interested. Okay. Do foundation models know geometry? Probing frozen features for continuous physical measurement. This is actually related to a tweet I was looking at. I know I said earlier flippantly, no, they don't. They probably do in some way. Okay, so we're not going to get a very good diagram for this. Okay, so a hand image, a frozen model, get some features. What? Text decoder and a linear probe and a LoRa. So what? Like what? Sorry, we're just going to ask it? Okay. A 6,000 parameter linear probe extracts hand joint angles at 6.1 degrees MAE from frozen features. Well, the best. Okay, I think I'm not going to say anything. Let's just move on. Okay, next. Maybe Semantic Scholar. Yeah, that's a good idea. I can experiment with a different viewer that pre-annotates. I think it does. To do this well, I need some tool that is going to help highlight things. And then my role becomes like more a voice and driver and interpreter for the highlights. Or maybe this is just a bad format. I mean, after we're almost done with it. After the stream, I'll just reflect. I'll rewatch it. I'll see what I think about it. I'll see if I think there's a good way to do it. I think some of these have been okay. Some of these have been bad. We'll see. Attend before attention. Efficient and scalable video understanding via autoregressive gazing. We propose auto gaze, which reduces computational cost of video understanding. Okay, yeah. Auto gaze. So are we going to downscale the tokens? What does that say? Let's see. Lightweight module that removes. Yes, we're going to remove patches. We're just going to straight up prune them out. Train with next token prediction. Oh, so it's like an autoregressive predictor. It autoregressively selects minimal set of multi-scale patches that can reconstruct a video. Oh, that can reconstruct the video. Eliminating the redundancy. Oh, so we're going to like think about the redundancy in pixel space and then pass them through for the understanding. And we're going to prune a lot of tokens in these videos. Interesting. Okay, so we have a predictor that prunes the tokens based on the visual loss under some threshold. And then we're able to pass through like 19 times fewer tokens. That's awesome. How good are the results? So it tends to target patches with higher optical flow. So it uses coarser scales to capture higher optical flow. So it more frequently selects patches. That's cool. So it tends to keep things with the motion. Yeah, good message, AMR Sala. I like to do them 8 a.m. my time Saturday. This is 4 p.m. my time. I just had a conflict. In general, I think it'll be much more friendly with your time zone. Let's see. Any more results that compare this? Yep, here we go. So the auto gaze, we can improve the performance because we can have more frames. Nice. Okay. I think I fit that last one into the speed date actually, which is good. Oh yeah, for any new viewers, what we're doing right now, I'm calling it speed dating of the papers. I spend 1 minute 30 seconds with each one. If I like it, I keep it. You can see a bunch that I've liked that I keep. Even if I don't like it, I might keep it. And even if I like it, I might close it. It's just papers I want to closer at versus not. This is actually not one I think I want to look closer at. I think we got it. Really cool method. You can basically have a bigger resolution and a bigger number of frames if you filter on frames more aggressively. And then you can get better performance. That's awesome. Full paper. No wonder a friend sent it to me. Okay, now I'm going to speed date a paper from a friend. Scale space diffusion, my former advisor and then 2 colleagues. I already know the idea behind this one, so we're going to go through it kind of quicker. Some of this is reminiscent of things like pyramid flow, and other ideas for like use smaller spatial resolution when you're using the noisiest latents, right? The idea is like don't waste all your computational power on a t equals 1000 latent. That's basically pure noise. Instead, resize it as you go through the hierarchy. The thing is, like, without insulting pyramid flow, because it's a great paper, the way they, first off, it operates in latent space. This operates in pixel space. Second off, the thing that pyramid flow does is almost a hack. It says you can just like upsample the latents kind of whenever you want to, even like by, I think one way is nearest neighbor down, and then it's bilinear up. Whereas this paper solves the math behind that upsampling in the pixel space. It is more of an academic style work in that when you look at the results, It's going to focus on like syllab A 64, syllab A 128. So like smaller resolutions typically than you would see in papers from industry labs where you're going to be 256 up to 1024. So they're not doing that, but I still think it's a good proof of concept to show that you can first off operate in the pixel space instead of the latent space effectively and more efficiently by allocating more compute power to the less noisy steps basically within your generation process. So you're simultaneously removing noise and upsampling with a diffusion process that mathematically is aware of both. And I think that's pretty neat. I'll come back and give the paper a little more love towards the end. That wraps up the speed dating. I'll keep the vertical stream live, but I am going to swap my OBS scene to the mixed. Which, what is that going to do to the vertical? Should I just kill the vertical stream? Maybe. I mean, now the vertical stream is just like audio. What happens if I click this? Can I like turn off the dual stream now? No. Okay. That's kind of a bummer. I'm definitely not going to end stream, but now it's just my voice like going through. Yeah, I'm curious. What time? So 8 a.m. Pacific to UK. I think it's 4 p.m. UK, right? Yeah, it's 4 p.m. UK. What about Middle East time? Like 7 p.m. Oh, so it is a nice time for like Gulf region. Okay, cool. It's good to know. Yeah, that is when I prefer to do the stream, to be clear to everybody. Like, I intend to do this 8 a.m. every Saturday. I was going to do it 8 a.m. tomorrow. My daughter's soccer game rescheduled like last minute. Not last minute, or I wouldn't even be here right now, but you know, like after I had already thought about when I wanted to do the stream, it rescheduled. So it's just forced us to do it in this time frame instead. All right, let's take a look at this guy. I can full screen now. Maybe I'll lean back in my chair the tiniest bit, and we can really take a better look at things. I will be mindful, by the way. I know my face is blocking like this bottom right part of the screen, so I'll be careful. Time to remember what all these papers are about. Oh, right. So they're just like exploring the tasks that they do. I thought this was interesting. So what I wanted to see during this longer time that we spend on it is, so I understand that they're initializing the image transformer with some text LLM weights. How big is that then? Like, are we talking about like a 0.6b text model, so a 600 million parameter vision model, which, to be clear, makes it comparable with like a VATH? Or like, what are we doing basically? I really want to know that. And I want to understand what this feature reconstruction loss is. Like, what features are we trying to reconstruct? And I realized that the LLM is kept totally frozen this whole time. I like the idea that this is synergistic training because it kind of reminds me of this of the column paper that we just looked at. Is that how people say it? Conference of Language Models paper that we just looked at, which basically says good information for the vision models is in the KV cache, but the LLM doesn't use it well. Well, maybe if you encode that with the text LLM, it'll be able to use it better. That's a good idea. I don't know if that's what's happening here, to be clear. It's just a thought. So 2D rope instead of 1D rope is good. That lets us adapt to images. 1D rope would basically assume, like I said earlier, the problem with like, you don't want your top left patch to think it is really far away from the patch below it, which is what happens with a 1D rope. But a 2D rope, they know where they are, right? And we could even do video if it was just like a 3D rope or some kind of thing like that. Or are they trying to do the video with the 2D? That's kind of interesting. They do say image/video input, so I'm kind of curious. Oh, and they still have a projector after the vision encoder, which... What? Really? Why? What? Am I thinking about this right? Why would you... Maybe there's just a mismatch in the feature dimension. Maybe you are initializing it with a smaller LLM, which would have a smaller latent dim. And so maybe the purpose of the vision projector is just to upsample the tokens. That's a thought. Okay, so built on the Qwen 3 LLM backbones available in 2D and 8 be parameter variance. Okay. They transform the LLM's causal self-attention into bidirectional full attention, which allows it to operate like a VIT, which I think they do just by eliminating the masking, which is like an input side thing, not a wait side thing. To support variable resolution inputs, we use 2D rope. Great. That's known. Text division initialization offers architectural expressivity to incorporate advanced design elements such as QK norm. Okay, but like you can do QK norm in a VIT. That, to be clear, there's nothing about a VIT that says you can't do QK norm. In fact, latest VITs have QK norm pretty much always. Native alignment. The vision encoder begins in representation space. I said that yeah, that seems like a good thing. The semantic priors inherits rich linguistic knowledge from the outset, providing strong semantic grounding for visual concepts. Okay, I'd like them to prove that actually. So we'll see what the evidence says. And then it's scalable because you can use established LLM design principles. I mean, we were kind of already following those for the VIT. So I guess what I'm saying is from all these 4 benefits, I only buy these 2. Not faulting them for the other ones, but like these are the ones that I believe probably matter. Okay, video encoding and projector. So let's look at that. I did say I kind of wanted to know how they did the video. I might need to actually read the text. We first partition the visual input into patches and map them to token embeddings through a linear projection. The resulting visual tokens are then processed by the vision encoder. For image inputs, when the token length sees the maximum context, we downscale the image. Okay, so they downscale the image in image space, it sounds like. For videos, they sample at a fixed sample rate, which is then capped at a maximum number of frames. If it sees the maximum number of frames, and we adjust the global input resolution based on the token limit while maintaining a consistent resolution across all frames. Our design explicitly prioritizes content adaptive granularity. I feel like for video, you could just do sliding window attention to handle however many frames, especially when you're already using Qwen 3. So they introduced temporal redundancy-aware token compression to allocate more tokens to the most informative frames. 4-stage comprehensive policy based on keyframes or intermediate frames. Keyframes have rapid change. Intermediate frames are stable context. So we have a global visual token budget, and we have a minimum allowable token per frame count. So the first stage is to maximize the information retention of the video. If the full resolution tokenization satisfies the number of tokens we're allowed to have, all frames are tokenized at their native resolutions. Okay. If the total token cost under full resolution is over the max, we downscale. Both key and intermediate frames are downscaled while maintaining a fixed relative ratio. Intermediate frames are 4x relative to keyframes. Okay. So the intermediate are a lot smaller. And we utilize the bilinear interpolation to resize and so we are just downsampling the frames like in pixel space with no learned transform. Cool. I thought they said 4 stages, by the way. Did they not? But now I'm seeing 3 stages. 4 stage. Comprehensive. First stage, by the way, is do nothing. And then there's no 4th stage. Okay. It happens. Sometimes we write these papers on deadlines. I'd say it's a 2-stage, right? First, we downscale the intermediate frames 4x. It didn't say concretely how they identify intermediate versus key. Maybe some kind of optical flow thresholding. Saturation or scaling. As it intensifies, intermediate frames may reach the physical lower bound. Because they did set a T-min, and upon reaching that, we clamp intermediate frames at T-min and transfer all remaining compression pressure exclusively to the keyframes, and we downscale the keyframes until the global budget is satisfied. So that's pretty greedy. That makes sense, I guess. All right. Construction of high-quality multimodal recaption and QA datasets. I don't really want to look at the data construction too much, do I? I think I did, actually. I wanted to see this. No, I didn't. That's a different paper. Okay, I think I've seen what I want to see from this paper, except for like the results, which I think we only glanced at earlier. So their 2B model compared to the Qwen 3 VL 2B is whoa, like what happened? Maybe they got some of the data or something. Still, this seems pretty decent. I like some of these data sets. Some of them I like less. All of these seem reasonable. And, oh, what about the 8B? Yeah, so that was the 2B. This is the 8B. Still looks good. I mean, it looks like it kind of trades with Qwen 3, and some of this could be a mirage in the sense that they could have just chosen data sets that they do well on and ignored stuff that the Qwen 3 VL does well. And it's also worth saying they're kind of like fine-tuned on top of the Qwen 3 VL in a sense. I'm going to see if there's other results. I actually do remember there's one more thing I wanted to see, which is like, what is actually the design of these encoders, the vision encoders? Also, do they have any tasks like that just the encoder does? Not VLM tasks, but like image tasks. We're into related work now. Okay. This will probably be at the top of their experiment section where they tell us like the design of implementation details. I wonder if it will work if they used a protein language model as the encoder. Is it really using semantics or is a transformer acting like a generalized computing device? Yeah, that's a good question. So you mean like a protein language model? You mean where like they're not predicting actual language tokens, but they're just predicting like cells or some like arbitrarily defined um, thing, not necessarily English. It could just be anything. And maybe other things will work even better, like protein or cells. That's a good thought. Sorry, I'm trying to find this. Like, I want to know the number of parameters actually is the main thing I want to know. Whoa, that is very interesting. I totally missed this before. They're trying to have it reconstruct VL3 SIGLIP this paper's features. That makes it a little weird to me, right? So the vision encoder is a small Qwen. It's a Qwen 3.6b, which is the smallest Qwen 3. So it's like, you know, slightly bigger than a VITL, a bit smaller than a VITH. It's a decent size. Um, this part is funnier to me the more I look at it, though. Why this feature reconstruction target? Or rather, are you not breaking a lot of the things that you thought would work really well about the language pre-trained encoder when you have this loss that tells it to model the same features as the image encoder? Do they have an ablation that proves that that's like a good way to do it and that shows maybe how bad it is when you don't do it? Without reconstruction, there it is. Oh, it's in some cases. Why did they bold this? Am I crazy? This is better, no? And this is better. Oh, using random init is interesting. So you don't actually benefit too much from the pre-trained. Yeah, you are right, Sam. I don't even think it's 450 million. I think it's 400 million. No? Like, I think this is a search string I can put in, and we'll get. No, is it not? Um, Nah, I feel dumb. Is it going to be on this page though? You might be right that it's 450. I don't know why I had 400 in mind. Are we going to? Oh, sorry, I hit the mic. Ow, that did not feel good on my hand. I don't think they're randomly going to put the parameters here, but yeah, somewhere in that 400 range. This is a little strange, no? It looks like we don't need the language model initialization. We also, I guess some tasks benefit from that reconstruction loss more than others. So it's definitely worth it. It's worth it on average. All these things are worth it on average. Oh, and we even look at different targets, right? Or, sorry, is this still like, are we using this encoder directly or are we using this encoder in the reconstruction loss? let's see. To compare Penguin encoder with the existing, we conduct LLM integration experiments. The Penguin encoder is pre-trained on the full stage 1 dataset and compare it against representative baselines. For fairness, we adopt the Qwen 1.7b as the unified LLM backbone. I see. So this is just justifying that in their setup, their encoder works better than these other encoders. They say even though they don't have very many samples to train on. This, to me, I suppose, is the most compelling. I'm a little confused at why we just have the Qwen 3 VL 32 BVIT and not the Qwen 3. Is there not a 1.7 VL? I'm searching that wrong. There is. Oh no, this is 1.7 base. What am I saying? Let's see. Qwen 3 VL. I mean, these are some 2B models, right? I feel like that's an experiment that would help a lot to give context here. Like, sure, this is the mismatched encoder. I feel like saying this is the total data size is a bit misleading too, because what? Oh, is this a result they're taking from the Qwen paper? Like, okay, because they do say this is our value. Well, no, aren't you aligning it yourself? Because that's what you said here. The LMM weights, we compare against representative baselines. For fairness, we adopt the Qwen 3 1.7b as the unified LLM backbone across all settings. So I feel like this. Oh, I see. They're talking about the original encoder pre-training, and then yes, the stage 2 is now all the same. The stage 3 is all the same. Duh. Okay, we're good. We're back. Yeah, I wonder why you don't use the one that matches. Maybe because it's just even worse. Or maybe those numbers are technically somewhere else in the paper. I guess they should be, right? Like if we scroll up, we probably saw them. Yeah, I guess that's this. The reason I don't see that is it's this. I mean, what I'm saying is I would have liked to see them train this with their data and their settings, because maybe they have like really good data and really good settings. And that's the experiment that would get me to say, yes, it's definitely not like the alignment of the encoder, the data, and the settings. Like there's something special that happened here. It would just give me a little more confidence. I still think what I'm seeing, it's cool as it is. We spent a long time on that one. I don't know if we'll spend similarly long on all of these. Yeah, this is going to be a skip. I'm not going to sit in front of the 3D paper more. What did I want to learn about this guy? I think I wanted to understand what the experts are and how exactly the router is architected. Because I see that the user gives a mask, which is actually encoded by mask encoder. So that's like the user's condition. The user can also give a reference and a base image and a text prompt, and those are all encoded separately. And then heterogeneous experts process these, then the mask repaint happens, then the latent mixture happens, then the routing happens? Huh? Okay, let's look closer. So, multiple multimodal conditions. They're all tokenized and projected to heterogeneous expert branches. They are? I see the conditions encoded and concatenated into one sequence. I then see that sequence go through the DIT block. First goes through a norm and a mod. Oh, which is like a backwards DIT, right? Normally the mod is at the end. No, it's not. No, it's not. I'm thinking of something different. Ignore me. Ignore me. I don't know why I said that. This is standard. Norm and mod. And then it's going through MLP and multimodal attention, and then a projection layer. The projection layer is new and learnable. The whole DIT is learnable with LoRa. Learnable with LoRa. I suppose the projection layer, it says fire means LoRa, but the fire on the projection layer can't mean LoRa because the DIT didn't have a projection layer with experts in the first place. So what happens in this projection layer? We have our hidden state. We pass those latents along with the original text and the image latent for the base, the image latent for the reference, and again the image latent for the reference passed to the mask. What is mask repaint giving to the mask module? Because then what we get is we pass all of these through the same layer norm and the same linear projection, which we tune with LoRa. What do they come from originally, though, if we're just learning a LoRa on them? Whose layer norm and whose linear projection were these in the first place? But regardless, we get still these separate features where they're all in a sequence, so we can easily like disentangle them just by chunking, basically. And then we're going to fuse them in some kind of learned way. And then we're going to pass them into a mixer that kind of splits them back out and has a loss computed. Oh, and we also have a masking loss on, I suppose, the masking output. And then we're going to do a routing selection. Based on some time condition policy, based on some top K. Man, okay. So the router assigns confidence scores and selects the top K experts to process each token. Where does it select the experts? Expert outputs are normalized, modulated, and fused through the latent mixture module, yielding denoise representations H prime, refined by mask repaint. I feel like I'm missing something from this architecture. I think seeing the experts that they instantiate will help a little bit. 4 heterogeneous experts corresponding to text, mask, reference, and base modalities. The text expert, okay, this is telling us their purpose, which I think is intuitive. Each expert functions as a lightweight adapter embedded in a DIT block. Oh, okay. The user-defined mask can misalign with the object boundary. To address this, mask repaint refines M at each diffusion step. Oh, so it like fixes your mask so that it can actually work well with the features. And it predicts a soft mask that adapts to the object contours and promotes smooth transitions between the edited regions. Oh, I see. So like maybe you give it a mask that's like a block, but like some of the things in there you shouldn't change. Some of them are the wall. And like telling the model to change those things is just dumb. Because if it changes them, it's wrong. And that's wasted compute. And so your mask is like, your mask repaint is fixing the mask. That makes sense. Qualitative comparison. This is just results now. Okay, let's see. Implementation. DIT style backbone. Interleaving routed layers every 2 to 3 blocks. Okay, so we don't have a routed layer every block. Each routed layer uses a top K expert routing with the shared expert activated for stability. The model is first fine-tuned following omni-control. Man, something about this, like if I saw the code, I feel like it would make a ton of sense. Wow, it's a Flux 1 dev backbone. That's heavy. They must have good resources. That's why part of why the results look so nice, though. It's this Flux model. I'm curious though how it performs compared to like Flux context or like just some, you know, purpose-built editing model. Seems like it's pretty good. I think I spent as long as I can staring at the diagram and understood what I'd be able to. I think to get like full clarity, I'd probably just need the code. Intern VLU? What did I want to know about this? Oh, I think I know. I think nobody knows intern VLU better than me. Nice. Oh, let's see. Okay, so they collect some open source data sets for text to image and for image text editing, and they list all of them. I wish they would list the number of samples right here. Maybe they list that somewhere that I can see pretty easily. But they don't. Okay, so what's the general data preprocessing? The synthesized data features varied textual annotations and covers diverse. Okay, but how do they do it? So, given the depth, we first apply general preprocessing pipeline for filtering, expansion, and deduplication, as illustrated in Figure 6. Okay. First, the preprocessing stage applies filtering, expansion, and deduplication to construct a high-quality source pool. Building upon this, two parallel branches are deployed to generate text-to-image pairs and instruction-guided editing data, respectively. So they get filter data, they do retrieval-based expansion, and then synthesis-based expansion. And then they take the expanded data and they deduplicate. And then that's their source data pool. And they can do concise captioning, dense captioning. Oh, wait, I'm reading this wrong. This is filtering. Then they do some expansion of the prompts. Then they do some dedupe to get a bunch of prompts. And images. Then they do concise captioning, dense captioning, human-centric captioning, and then just lots of different captioning, and then they synthesize images on top of that. So the two parallel branches generate text-image pairs and instruction-guided editing data. Oh, so this is the text-image pairs, where most of it is like recaptioning, but then some of it is image synthesis. And then also they can generate editing data, where you'll either do it global level, so you'll generate instructions and then edit the image to have the data, or object level or attribute level or compositional, and then you'll verify. You'll verify that it followed the construction, that it was consistent, and that it had quality. And I suppose during verification, you either redo if it was bad, or you just throw it away if it's bad. That makes sense. That's a pretty cool pipeline. I wish they would show us maybe some stuff that gets thrown away. But that's not really clear to me. Oh, cool. Text editing data, text rendering data construction pipeline. Okay. So let's see. For synthetic text rendering, we prepare mask images, font colors, font styles, and adaptive layout options during the rendering. These attributes are randomly sampled, and the text is around typography that adapts to its length. What? Oh, wow. Okay. So this is how they put like text data in images. They need a mask, a font, a color, and then a layout. Okay, that's interesting. That's how they get data for the model to be able to make like diagrams with text in them. That's very fascinating. Text editing, data construction pipeline, anything neat here? Identify candidate text regions for editing, original image, some OCR, some test score, some filter flow, select the editing area and generate the edited text. Okay, so first they find the text, then they generate the edited text, and then they generate the edited image. So nice three-step pipeline. Identify the region of the image, some example text, edit. Okay, so very like I speculated during the 1 minute portion of this paper, tons of stuff in the data synthesis pipeline. Do they tell us the order of magnitude here? Is it millions? Is it billions? Doesn't look like they released the data. The data is always the secret sauce, and it's the part you'll never see anyone actually release. Fun stuff. What time is it? I think I need to run to the bathroom real quick if I'm going to continue the stream. And get some more water. I finished my whole water bottle. So I will be back in like 2, 3, 4 minutes. Just refilling my water. And muting. Okay, I'm back. Okay, there we go. Video's back. I got ice cream because this is like surprisingly tiring. You would think it's pretty easy to just like sit in the chair and ramble. But it's kind of hard. Okay. What did we want to know about this one? So yeah, their whole thing is like we can tokenize for a latent model, for a world model in 8 tokens. So the main contribution is the tokenizer that compresses each observation to as few as 8 tokens. And then they have an action condition world model that can plan, where like you tell it the action, you give it some original frame, and it predicts the tokens corresponding to, you know, the future frames based on the action that you told it. Or they call that planning. I don't know if I would call it planning, but that's what they call it. I think they call it planning because it's like I don't know why they call it planning actually. Just because they're autoregressively predicting states maybe. Like the model predicts one latent state, gives it to the next, gives it that state to the model, and then it keeps going until it gets some idea. And that is the thing that they optimize. Um, let's see. So yeah, it's trained just as like a regular tokenizer, right? What's the special sauce in how this tokenizer is actually trained? Ah, this is the part that we ran out of time for when we were doing the speed dating, right? Is the tokenizer architecture detail. So we have an encoder and a decoder for the VQGAN, which we're not going to touch, right? And we treat the output of the VQGAN encoder as our target latent, which tells me that we're doing some kind of distillation. We're going to mask those tokens according to some masking ratio. If the diagram's to be believed, it's like 50%. And then we are going to pass them through or to an MMDIT. And from that, we expect to get the unmasked VQGAN latent, which we can decode with the VQGAN to the image. Their encoder's role in this is to predict this latent condition for the MMDIT. And they predict that by resampling and then FSQ, which is quantization, on the DynaV3 tokens. Oh, and I suppose their latent resampler has like its latent representation is like a learnable input, and it's going to perform some cross attention with these dyno output tokens. That's what this looks like to me. Let's see. So where's decompact? Oh, this is decom. Okay, so this is the encoder, this is the decoder. So are they saying that they just encode to their latent space, which is tiny, and then they decode to the VQGAN space, and then they decode the VQGAN to image? I think that's my understanding of this architecture. So we do limit the size of the latents. And I think the point of this masking is to get to where our model doesn't need VQGAN input tokens. Or we can provide the VQGAN tokens at inference time just as like some kind of learnable noise. I'm not sure. I'm trying to understand how we get rid of this branch. Because if we can't get rid of that branch, then we actually have a big latent representation. Or maybe the point is that the thing that our planning model interacts with and has to predict is just this. I'm not quite sure. I will try to understand that better. So yeah, conventional tokenizers encode images hundreds of tokens, which makes their sampling slow and autoregressive rollout. So they encode it in 16 or 8 discrete tokens and avoid iter denoising by using a discrete latent space. Okay, so the key principle is to preserve only planning crucial information while discarding reconstruction-oriented high-frequency features. So they build around a pre-trained DynaV3. It's funny they say that because the DynaV3 actually has like some ability to reconstruct high-frequency information as well, right? Like you've seen it in the representation autoencoder paper where you can train a linear layer on the DynaV3 output to reconstruct the original image. Some pixel details are there, some aren't. But it maps an image O onto a sequence of n discrete tokens, which we saw in the diagram. Each selected from a vocabulary size k. Remember, it's discrete, so we're going to have like a code book, right, with a certain number of like with a fixed number of tokens, depending on whatever we determine the size of our code book to be. The encoder architecture consists of, yeah, we already saw that, a latent resampler with we saw learnable query tokens, and then the FSQ layer. Okay, we know this because we saw it in the diagram. So direct pixel reconstruction is an ill-posed problem. Yes, because the information bottleneck doesn't let perceptual details flow through. So they produce an intermediate representation, generates latent tokens from a pre-trained tokenizer using the compact Z as a condition. So the pre-trained tokenizer is the target tokenizer because its tokens serve as the intermediate targets that bridge semantic representation to pixel space. Oh, so their semantic tokens that can be used for world model planning are like an auxiliary semantic representation. The pixel generation is still driven, it sounds like, by this original pixel encoder. And so now theirs are just used as the condition for some conditional generation. Okay, world model in compact latent space. So they train their world model directly in the end token latent space given a data set of observations and action sequences. We encode all observations to compact tokens. And then we use the mass generative modeling to train the world model. The training objective is log PZ alpha. What's the alpha again? Do we have this? What? Or is that like the diffusion alpha? No, what is that? What is alpha? Oh, the action. Okay. So we get the latent and we try to predict the next latent given the current latent, the action, and M. Sorry, I'm going to blame my tiredness on the fact that I can't immediately recall what M was. Masking. Okay. Oh. So we do mask the target latent, and that's one of the inputs. And then we're just minimizing the expectation of the log. Okay. During model predictive control, it can now perform rollouts using only N. Yep, not too many tokens, enabling planning latency that was previously intractable with 100 length tokens. Yeah, because it can just predict next state from current state. It doesn't need a history. It just needs current state, and then it'll go to next. Since the specific choice of world model architectures are orthogonal to the token design, any model capable of modeling discrete sequence distributions can be employed. So it looks like it's a two-stage training, right? Like we're going to first train this whole thing to actually train the encoder, the compact encoder decoder, but then when we're training the latent world model, which is Fi, we're just going to use the compact encoder to get the compact tokens. And we're going to try to predict the unmasked. Oh, we're even treating like the last token as like, okay. So we're treating the latent world model training as like a masked prediction task. And then when it's time to actually roll it out, yeah, we give, obviously it expects the, like whatever latent step is trying to predict, it expects the last one as a condition. That's what you see here. It's getting passed as a condition. It also expects like the latest action. I'm trying to understand what happens to the input though. Does anybody see? I guess I have two viewers right now, but like if one of you understands that, let me know. I feel like I'm missing that key detail. How are we doing inference when originally we trained on a masked version of our output? That's, I think, the one question I have. If I was at their poster in real life, I would just ask them. I'm not, so I can't. Okay, so this is their reconstruction performance when they're used in conjunction with the MaxGOT VQ GAN. So this should always be treated as an upper bound on their result, probably. It is interesting to me that their inception score is higher. Kind of strange. Maybe it's the result of injecting the extra semantics from the Dino v3. That could cause the inception score to go up, I suppose. But otherwise, the reconstruction FIDs are worse. That's not surprising. However, it is worth mentioning there's a big discrepancy in tokens. So we forced a pretty big bottleneck here. What I'm missing a little bit is what we do here at inference. I'm still missing that. On both sides. I'm missing it here, like what the inference looks like here. I'm also missing what the inference looks like here. Those are not clear to me at all. But it looks like overall we get decent results. Or they get decent results. Yeah, I think that's a good deep dive. I don't know why I'm spending so long on these papers. Ironically, it might be because I am tired, like mentally. And so that causes me to just sit in front of one thing for a little longer because it's sort of comfortable. Okay, yeah, I wanted to understand this a little bit better. So yeah, we can have the bidirectional diffusion model where every token attends to every other token for any given clip we're generating. Or we can have the causal AR where, we're masked and we're predicting next tokens. But apparently they're saying when you try to do the rollout, oh, with the clean context. Okay, well, you need to handle this isn't necessarily fair, right? There's this clean context issue where, like, your model's trained on the clean context, and so it'll accumulate error over time in real inference. And that's what's happening here. And so you're always telling it things are clean, and it's trusting you, but things are really, like, a little noisy each time, and eventually you just diverge into total noise. There are workarounds to this, by the way, which evidently is what this is. This is one solution for the quality degradation. And obviously the issue of the bidirectional diffusion models, there's no rollout. So they have rollout without the degradation. Many papers have different ways to solve this. Yeah, we looked at this before, and I said that it looked like what was happening was that, like, when we're in the context, we're not, like, looking at the clean last video in context unless we're at the clean step. When we're doing the, like, very high steps, the very noisy steps, we're going to look at the last part of the video or, like, the last chunk of video also at that same phase. That's what I think I see here. So they do causal generation across all blocks within each denoising step, conditioning on context to the match noise. Yeah, context at the match noise level, which is really interesting. So one problem with that is, like, when you do this, you actually have to be careful about the order in which you do it. Like here, the order makes a lot of sense. You generate denoise all the way, and then you can generate the next. With this one, you actually can't do that because you would be storing so much crap that you need access to in the next step. So you sort of have to do both of these at the same time, like these here. Like you generate this, and then you can take that and start generating the next, and at the same time generate the next step here. In this way, it's very reminiscent for me of Magi attention or Magi 1, Magi, I don't know how they like to say it, Maggie, maybe, M-A-G-I, where they are, like, starting to denoise some chunk, and then when they reach some level, they then start to denoise the next chunk. And so, like, they do the AR prediction of chunks, and then the iterative denoising, but then the AR is initially using, like, this still partially noisy sample in the context. I want to be very careful saying mean things about papers. To me, this almost strikes me as the, like, less engineered version of that. Like, maybe this is the more theoretically satisfying version. But maybe it's worse. I don't know. Because the nice thing about the other one is that within chunks of that diffusion denoising pipeline, you can have bi-directional attention, which is pretty nice to give you consistency in video, where it's not necessarily nice to say that the last frame depends on the first frame, because in some sense the first frame equally it depends on how you want to look at causality, but it can be nice to look backwards in a video if you want to generate a good one, is what I'm getting at. Maybe it's the same you could argue in sentences. It's nice to be able to look at the end of a sentence sometimes to fix the start. I don't know. These are arguments that people will have. Should it be causal? Should it be bidirectional? Bidirectional is obviously very expensive. So then it's like, well, if bidirectional is better, do we, protect it in some way? Like the Magi 1 paper doing, like, chunks that can be bidirectional. Okay, so motion dynamics under bidirectional and causal attention are strongly positively correlated, so regularizing the former effectively constrains the latter. Oh, so they have a bidirectional attention mode. Kind of like I was saying. What does that mean? I'm not seeing it quickly. And I don't really care quite enough to look. Um, yeah, I think we mentioned before, it compares very favorably in terms of throughput as well as the quality to some of these prior works. Although the backbone is not going to be the same, I think, because I don't think they re-implemented these works, and they're using a backbone that I think is like contemporaneous with the prior works. That's kind of a confounder. I'm not positive, by the way. I'm not going to look super close at that, so don't like take my word for it. If you really want to know, you'd have to like look really close at the detail. But that happens a lot in this space. That's why I'm just going to say it. Like you'll see a lot of the time people compare with the 2023 paper. They'll just take the number from that paper. They won't mention that like they have a 2026 backbone and that paper has a 2022 backbone. So it's kind of hard to get the fair comparison a lot of the time. Here they just compare how they don't like CosVid. Yeah, so CosVid, you see the degradation. This is because of error accumulation. The video is actually getting noisier over time, and so it can't generate a clean output because it's just getting noisier. Causal forcing has the same issue. Self-forcing doesn't, but evidently with the self-forcing, some drift happened that they're telling us is bad, right? Or actually, this is just degradation. That's interesting. This is degraded. This is somewhat degraded. So the self-forcing degrades too. It's not as clean a fix, I guess, as you might think. Interesting. Okay, it's good enough for now. Why did I want to look at this more? Oh, did I want to understand better how they're doing the inputs? I think at one point in time I did, and I think now I don't. So yeah, I think I'll go quicker through these last papers just because chat's pretty dead at this point. I think 4 p.m. is an okay time to go live for me. I think 6 p.m. is a really bad time to be live now. Oh, I know what I want. Hopefully the ads aren't crazy. Ew, what? No, just chill, chill. It's late on East Coast. It's a Friday, so like people with lives are doing things. Past midnight in Europe. It is morning in East Asia, but I don't know if I have a lot of viewers in East Asia. And so we're just kind of late on East Coast, and we are like not workable at all in Europe or North Africa or the Middle East. I don't know. I do pay attention to the metrics is basically what I'm getting at. I don't know. Trying to have goals around that is a little weird. How do I read papers good is sort of like the big question. Okay. So one model, mini budgets, elastic latent inference for diffusion transformers. Yeah, I wanted to understand this one better because I wanted to understand this. Like what is happening? Where we can get latents of different length, like different number of tokens. I understand how we could trim the latent dim. That makes sense. But how do we eliminate tokens? Because the VAE tokenizes the image spatially. So how can we just cut off parts is what I want to understand. So a lightweight read write across attention rows, a short spatial DIT processes patchified inputs, read pulls information to the latent domain where core blocks operate, write broadcasts updated latents back to spatial tokens, and a small spatial tail produce output. Spatial tokens and latents are partitioned in corresponding groups, with cross-attention operating only within groups. During training, we randomly drop tail latents, yielding an importance ordered interface. At inference, the number of latents serves as a user-controlled compute knob. That part's cool. How? From spatial tokens to allow flexible distribution computation, we introduce a minimal change that eliminates the fixed mapping between tokens image patches as shown in Figure 3. I don't understand this from looking at Figure 3. We create a latent domain by instantiating a latent interface of k tokens. To map the original spatial domain to the new latent domain, we use a lightweight read cross-attention layer following 12, which enables the model to select the number of latent tokens and adaptively for each spatial region of x of t based on the difficulty. This forms a compact latent domain on which most transformer blocks operate. Oh. So this still looks spatial to me. Because it still looks like we're going to, so basically we're remapping these latents into these latents inside of this groupwise cross attention. But it looks like we're still going to have like same number. Like this doesn't look incidental to me. It looks like the shape assumes that our tail is always going to be roughly the same size. Not roughly, exactly the same size. And so like we're either dropping one token or in this case 2 tokens from all of them. And then we're using the cross attention to shove this into this, this into this, this into that, this into that. But it looks to me like it's still going to be basically spatially correlated. Which means now I understand everything I wanted to understand. Oh, I do want to know what MB is, so I can understand the table. That really threw me off earlier. This is a dirty way to try. Multi-budget. Oh, it's right there. Oh. So they have their elastic latent interface, and they also have the multi-budget. Where do they explain multi-budget clearly? We aim to build a multi-budget model since usually it summarizes group information via the read. A subset of tokens can still predict for the entire group. Thus, we train an importance ordered latent interface where earlier tokens in each group capture globally useful. Later tokens are fine. We enforce that with a simple random prefix keeping scheme. Head latents are seen more often, forcing them on to storing the most important information in earlier latents. I still don't understand how that makes it multi-budget. That does not explain the multi-budget part to me, I don't think. Why don't they show the ground truth? Or are these generated? Oh, these are generated. That's funny. That looks like there's a picture of a fish guy in ImageNet that this looks almost exactly like, except it's like just been made weird. So I assumed it was reconstruction, but no, it's generation. That's funny. These images have a very like not cartoon is rude. They have a certain sheer or sheen or like a veneer that like they look unnatural in a very specific way. Like he's shiny. Why is he shiny? This is supposedly trained on ImageNet. How did they make it shiny? Normally, I feel like you see that when they're trained on like synthetic data with like high aesthetics, filters and stuff. Not what we were looking at just there. Anyway, let's go back to the main paper. And now that I understand this table, I can read it. ELIT and MB are both theirs. Somehow they both just make it more expensive. That's a part that confused me. Because I thought, we're using smaller latents, so we can make it faster. But perhaps they scaled it up to make the teraflops comparable. But I expected speed ups, which is why I'm confused. But I suppose they're saying it at basically equal teraflops. We can reduce the FID a little bit. A lot for the DI2XL. Although, how did we get this result? 5.7. Like, that's not the main paper result. How would we... Maybe they train it for less time or something. Yeah, maybe they train it themselves, and so we're looking at like an undertrained DIT, and that's why it doesn't line up that way. Basically because I'd expect this number to be like 2.3 or something, whereas 5.7 is a lot higher than that. So it makes me a little bit skeptical of their number if they're just doing this recomputation. Maybe this is an advantage that like vanishes once you train the model properly. That's something that can happen with a lot of this kind of paper. So this is what happens when you start to cut tokens from their method. At full tokens you get this, and as you cut tokens it just we can zoom in. So full tokens remove tokens. As you remove tokens you lose detail. That's what we see with this turtle boy. All right. I think that's enough time with this one. We figured out pretty much how it worked. We were able to understand the results. I did want to try to understand the adaptive length video tokenization a little bit better, but man, I am getting like tired. Tired like nobody's business. Let's see. So it looks like we train a proxy tokenizer like on all possible latents basically. So like we have these candidate assignments where like these are just different ways to tokenize the set of images. And originally we train it to work and handle all of them, and then we train a router to learn what the optimal assignment is to be able to get the best reconstruction of the video. Let's see. The architecture of the 1D variable length video tokenizer. The video input is spatiotemporally patchified into 3D embeddings. That's here at the top. According to the given assignment, where the assignment is essentially supposed to be the budget to the tokenizer, we initialize these 1D queries. So these are like learnable queries. We can have a set of learnable queries depending on the assignment. We can have more learnable queries when we want to have like a bigger representation for that video, which is something we'll figure out later with the router, right? But we have to have a bunch of different sets. So we'll just initialize it at train time with some set. At evaluation time, it would be with whatever the router says is the optimal set. Then we will pass both all 3D tokens and these 1D queries through. When I say 3D tokens, I mean like height, width, time, right? Video tokens and 1D queries through the Q-former, which is like a lightweight attention projector, cross attention projector here, because we're trying to do cross attention between our video tokens and our 1D tokens so that we can basically shove the video tokens into the 1D tokens. Then we're doing VQ, which is vector quantization, to get discrete tokens. And how do I use that to recover my 3D queries? According to an assignment A, 1D after keyformer encoding and quantization, 1D discrete tokens are produced, yes. Finally, 3D queries are initialized to reconstruct the video frames from the 1D tokens. I don't understand the purpose of this arrow. This arrow confounds me. But my assumption is that these are just learnable 3D queries corresponding to the length of a video in a chunk. And when we pass in the discrete queries and the 3D queries that were learnable, we get back 3D patches that we can depatchify, and that's the video. I'm really struggling to understand why I'm seeing the arrow here and here, though. So maybe I can find that out in the text. That's like, I think, the last thing I want to understand about this paper. Okay, the 3D queries for the decoder. The 3D queries are initialized using the first 1D token in their corresponding temporal block. Oh. So we take the first 1D token, and we initialize all 3D queries. Oh, is there some predefined temporal alignment here always? And so like these blue are initialized, like that's one chunk of the video, and those are initialized with this guy, and then these green are initialized with this guy, the yellow with that guy, and the red with that guy. I think that's what it's saying. That's cool. And then we actually pass it through the decoder. Okay, the router. I also want to know the router design. So I lied when I said that was the last thing. What the heck is this router? Oh, okay, got it. VITS, perfect. So pretty small, not too heavy, which is good because the whole point is we have lower budget because we're going to process the video with fewer tokens, right? That is totally defeated if this is a large model, processing these all at full size. So it processes them at full size, but it's a small model. And a small model can still do the job of saying, how much tokens do each of these need in order for us to handle them effectively. Great. I understand this now. Wish I could have done that in the 1.5 minutes, but some things take, closer to 5 or 10 or however long I've been looking at this now. It is what it is. If you're just in the stream now and you didn't see, we started the stream by going over all these papers and more for 1.5 minutes each. I tried to do my best to summarize them in that time, blind, like I had never seen them. Some of them I did a really bad job. But part of the point was to filter and like pick papers that we could spend more time on. And that's the list that's remaining, is like the papers I actually wanted to take closer looks at. By the way, it says I have 3 concurrent viewers. Chat's been quiet for a bit. If anyone that's here could just like push 1 in the chat, it would be helpful just to know that I'm talking to like real human beings. Also, let me know if you're watching from the vertical shorts feed, because I've been running that this whole time. I'm not sure if anybody's clicked it, and I'm very curious, because right now it's really suboptimal. Earlier in the stream, I was doing a segment where like I had, I'll show you. I had this vertical scene, and with every paper, I had them like this. So like even in the vertical stream, you could see the entire paper. I did that for like 30 minutes. But then for this part where we're reading the papers for longer, I switched away from that. Anyway, next paper. All right, one OmniStream. I think this is the one where I complained that I couldn't tell what the streaming aspect of it was. So let's try to figure that out now. We have an image, a video stream, a 3D scene. These could be our inputs. 3D rope. We get a class token, a cam token, and we train it to do like depth maps or static and temporal representation. Like we could train it to match like what are the teachers actually? Earlier, I think I thought that was a pixel loss, but it's actually like a Dino v3 distillation. Oh, wow. It's actually Dino plus LBot plus Colio plus Lgram, which is literally it's just Dino v3 loss. This is Dino v3 loss. That's what they're actually doing. I did not realize that. Oh, and the teacher is actually just an EMA of the student. Sorry, I totally did that wrong when I went over this originally. Yeah, I totally missed this in the first place. Dang. I thought it was a distillation thing. It is, but it's like Dino distillation, not distillation. Depth map, Bray map, vision language alignment. Yeah, but I want to see how do you do streaming? Like what is the KV cache? Under the BF causality, inference can be performed incrementally. When the frame T arrives, it computes queries and reuse cache. Okay. So they do nothing new for the streaming. They can just use streams with existing stuff. Okay, that's all I want to know. Next. I want to know how they train this. This looks cool. Where for later video chunks, we don't need to do as many steps because we already did the hard part when we constructed the original context. But I want to understand like what the diagonal forcing is. So they explicitly model the diagonal denoising trajectories during training through controlled noise injection. This approach ensures temporal coherence across chunks while minimizing error accumulation by conditioning each new chunk on the final noised state from the previous chunk's diffusion process. Specifically, the conditioning input for chunk K is derived from the clean output of X sub of chunk K through a noise injection operation. So X sub K minus 1, that's clean, which we rescale according to some alpha, and then we add noise according to some other alpha. But the alpha is not in terms of T. These aren't like time condition alpha. This is like a chunk-based alpha. So we denoise relative to whatever chunk we're at. That's interesting. And now I feel like I understand it. And I don't have concurrent viewers right now. I think we just dropped to 0. So I might just call it here, actually. I'm a little tired. Not quite in the mood to stream to 0. And this is the second time we've hit 0, so I think it's safe to say we're going to be dead for now. It's really late US East Coast now. I think it's got to be like, yeah, 9:30. I love the idea that this could be like really chill content that people could do when they're winding down, but I think that's not how a lot of people would probably approach it. It's like you are coming to try to learn this dense technical stuff, and you don't really want to do that when you're trying to relax. But anyway, I had a good time streaming. I'm basically doing this outro in case anyone watches the VOD. Thanks for anybody that came, and I'll be thinking about how to make improvements for the next one. Take care. Bye for now.